All right, guys, now we're going to be getting into OSPF, the Open Shortest Path First Protocol. I'm going to be providing you guys as much detail on OSPF, probably more than what we saw with EIGRP, and certainly more than what's in the course content, because we could spend a day and a half just talking about OSPF. In fact, in the traditional route class that we had for CCNP route switch, we would spend at least a day and a half talking about OSPF. OSPF is an IETF protocol. It was developed very shortly after EIGRP was, and it is a linked state routing protocol that is based on, or the algorithm itself is based on, what we call the shortest path first algorithm, or the Dijkstra's algorithm, which was actually developed by a programmer, Edgar Dijkstra, and was adapted. That was a decision tree process that Mr. Dijkstra invented that allowed us to kind of create this process of analyzing choices and making the best choice based on the shortest path first algorithm, which was adapted to OSPF and is used today in OSPF to identify the shortest path to destinations in the topology. All right. Now, OSPF, just like EIGRP, does provide a loop-free topology. But that loop-free topology in OSPF is not based on things like successors and feasible successors and doing feasibility condition checks. It's simply based on the fact that OSPF routers get to see everything. We exchange what we call link state information. So every router within the autonomous system, whether it's within an area or outside of an area, will exchange its link state information, meaning it's, what are the state of the links that the router is attached to? What are the networks or the prefixes? What is the subnet mask? And so on. What is the bandwidth and the cost, etc. All of that information gets propagated to every node within the topology, and then eventually we build something called the link state database. And a link state database is a kind of a compilation, if you will, of all of this link state information. So generally speaking, OSPF routers tend to make better decisions on how to reach a destination when they're trying to decide which path they should take. They don't do routing by rumor like EIGRP does. They make their own independent decision based on a complete topology of the network, if you will. So that means that the database is going to be a little bit more complex than what we see in EIGRP, number one. Number two, it's going to require more resources because we're collecting a lot more information than we saw traditionally in like an EIGRP protocol. So what we're going to be talking about in this section here is how do we deal with OSPF, specifically in a multi-area design, what we call a spine and leaf design, where we have an area 0 which acts as the spine of the network, and the non-area zeros which act as the leaves of the network. We're also going to talk about different network types in OSPF. And there's actually 6 different network types that exist in OSPF. There's broadcast, there's non-broadcast, multi-access, there is point-to-point, point-to-multipoint, point-to-multipoint non-broadcast, and loopback. So we'll talk about what that means in OSPF and how OSPF routing decisions and how timers are based on what type of network type OSPF is dealing with. We'll also talk about what the DR, the designated router, and the backup designated router means in OSPF, specifically in a broadcast network, although there are a couple of other network types in which we do a DR-BDR election, but mostly it's going to be in a broadcast environment. How do we modify the timers in OSPF? Unlike EIGRP, the timers in OSPF have to match in order for the routers to form an adjacency. So there may be scenarios in which we may want to modify the timer values, but we need to make sure that they match. There's actually scenarios in which you would have to modify the timers if you have mismatched network types, because certain network types use longer timers than other network types. So we'll talk about that. And then we'll finally wrap up by talking about what is the impact on OSPF if we have an MTU mismatch. And that's where you kind of stay in the exstart and exchange state, and you kind of keep flapping back and forth between the exstart and the exchange state, and you never go to a full adjacency. So there's a lot of interesting stuff here. I hope that we'll get into some of the basics as well to kind of fill in some of the gaps that you might have, with the lack of maybe doing this in the past, or maybe it's been a while since you've looked at OSPF. Okay, so OSPF, like I said before, is a link state routing protocol. Every link that's attached to every interface on every router gets advertised to the peers, and that information gets compiled into something called a link state database. And the descriptions of those links, as like what type of link it is it a point-to-point link? Is it a broadcast link? What is the cost of that interface? What is its relationship to the different neighbors that exist in the topology? In other words, is it attached to multiple routers, or is it attached to a single router? All of that information is compiled into the link state database. And we can verify the contents of that database by simply doing a show IP OSPF database, or drilling down into the database by looking at other specific database elements. Like if I'm going to look at the type 1 LSAs, I might do a show IP OSPF database router. If I'm going to look at the type 3 LSAs, I might do a show IP OSPF database summary, and so on. So hopefully we'll get into discussing the different types of link state advertisements that exist as well. There are primarily 7 different types that we talk about on a regular basis, but there are more than 7 different types of link state advertisements that can exist. OSPF is probably one of the most widely used interior gateway protocols. Number one, it's an open standard protocol. Like I said, it's an IETF standard, Internet Engineering Task Force. And because it is an open standard, a lot of companies and a lot of organizations choose to use it because they don't want to be tied to a particular manufacturer. They don't want to be tied to a particular vendor. There are other benefits to OSPF as well. I mean, it is a highly scalable protocol. It is highly configurable, but on the flip side, it's also a lot more complex, and you have to have a really solid understanding of how to implement the protocol in order to be able to do it efficiently and correctly. Okay? OSPF was developed to, in essence, address a lot of the concerns that we had with traditional distance vector routing. Remember, distance vector was where we started. IGRP was the very first IGP routing protocol, and then we got into RIP, and then we got into EIGRP, and OSPF came out after that. There are some huge advantages of OSPF over some of the legacy protocols. Certainly the speed of convergence and the scalability are huge benefits, but overall the protocol is just much more robust and much more flexible in its configuration. Well, I wouldn't say flexible necessarily. I think I would describe it as customizable, but there is a little bit less flexibility in that you have to have a very specific design. Okay? So what does OSPF do in order to function, right? Well, the very first step that has to happen in order for OSPF routers to exchange any information is we have to form an adjacency. The routers have to become peers. Just like in EIGRP, I don't exchange anything unless I'm your neighbor. And with OSPF, that neighbor adjacency process is actually even more kind of stringent, if you will, in that it requires certain parameters match in order for the adjacency to form. Hello and dead timers have to match. The area ID that the interface is in has to match with the peer. MTU has to match. Common subnet, just like EIGRP. Authentication properties have to match. We do not have an autonomous system in OSPF. We have something called a process ID. So that's one thing that doesn't exist. But again, there are some very specific elements in the configuration that have to be configured similarly or the same in order for the routers to form an adjacency. There's two ways you can implement OSPF. You can do it as a flat design in a flat network, basically just putting all the routers and all the interfaces into a single area. Or you could choose to implement OSPF in a multi-area design, like a spine and leaf design. We'll talk about some of the design limitations when you're implementing OSPF as a multi-area design, which is what you guys are doing in your lab exercise. So it says here that OSPF performs the following functions. Number one, it creates a neighbor relationship by exchanging information. Sorry about that. So OSPF performs the following functions. Number one, it creates a neighbor relationship, and we do that just like we did in EIGRP by exchanging hello packets. Those hello packets are sent on a periodic basis, every 10 seconds on most OSPF networks, and then every 60 seconds on some other networks. We'll talk about that in more detail a little bit later on. There is a dead timer in OSPF as well. That's the timer that allows us to determine when the neighbor relationship no longer exists because we've lost connectivity to the peer. And the dead timer in OSPF is typically 4 times whatever the hello interval is set at. So if it's 10 seconds for the hello interval, the dead timer is going to be 40 seconds. We propagate what we call LSAs. An LSA is a link state advertisement that contains information about the link itself, prefix information, cost information, etc., and the state of that link, which is what is the relationship that that link has to the other routers. In OSPF, the router ID plays a very, very significant role when it comes to analyzing the OSPF topology. In fact, you guys probably saw when you were doing your exercise that the router ID kind of shows up in just about every output that you have. Show IP OSPF neighbor, show IP OSPF database, show IP OSPF interface, show IP OSPF. All of these commands reference the router ID in some form or fashion. So when they say the description of an interface and its relationship to neighboring routers, they do that. They identify those neighboring routers by their router ID. We flood LSAs to all of the OSPF routers in the area, not just directly connected routers. Now, there are scenarios in which we flood information to a single router, and then that router is responsible for flooding that information to the remaining routers in the topology. That's an example of where we have a DR and a BDR scenario where the designated router is acting as the kind of central point of management for a particular multi-access network. We'll get into that later on when we get into the DR-BDR election process. We piece together all of the LSAs that OSPF routers generate, and we create the link state database, which is in essence the OSPF topology table. It's going to look a lot different than the topology table does in EIGRP. The database is a lot more complex. Hopefully when we get into the advanced routing discussion, we'll have an opportunity to kind of take a look at some of those databases. We use the shortest path first algorithm to calculate the shortest path, basically by placing myself at the center of the network, logically speaking, and then I start to calculate all of the different total path costs to each of the destinations within the topology. The biggest difference here between what we're doing here with as opposed to distance vector is that in distance vector, I'm making decisions on how to route based on how my neighbor decided how to route. But with link state protocols, I make a decision about how to route because I have a complete picture of the topology. The analogy that I often use to describe that is to say, if I'm driving down the highway and I'm trying to reach a destination, maybe I get on the 5 freeway here and I'm headed to Burbank. I see a road sign that says Burbank is 40 miles and it's in this direction. That is equivalent to a distance vector routing protocol. I have a general idea of what direction I need to go, and I know how far it is, but I don't really have any visibility of the path itself. I don't know beyond just the direction, which is the vector, and the distance, how to reach that destination. Whereas a link state protocol would be like opening up my Google Maps or my Waze, putting in the destination, and then being able to choose a path based on certain criteria. You know, I want to avoid toll roads or construction or traffic or whatever, and I can make a better informed decision on how to reach that destination because I have a complete picture of the topology. As you can imagine, the latter, as opposed to the former, is going to require a lot more resources. It's going to require a lot more information. Okay? Routers send out LSAs immediately. They're called triggered advertisements to advertise whenever the state of any link changes. We don't do periodic updates with OSPF, with the exception of flooding the LSAs every 30 minutes. That's called a paranoid update. And it's basically there as a synchronization process to synchronize the databases just to make sure everything is set up the way it should be and so on. All right, but otherwise the protocol itself is incremental, which means that it's only going to send out updates when the topology changes, and it's going to send those updates to the routers that need to see them, as opposed to everybody in the topology. Okay, so this topological database, this link state database, is really just the big picture of all of the links in the topology, what devices those links are attached to, what the status of those links are, and so on, which is why it is called link state. All right, we contain really a composite list of all of the link state advertisements in the area. Now, that doesn't mean to say that routers outside of a particular area can't reach links within a different area. In a multi-area design, we certainly can do that. It just depends on how those links are represented. For example, internal link state advertisements are what we call router LSAs. Those are what we call type 1 LSAs. Those type 1 LSAs represent the links within the area. And those type 1 LSAs are intra-area LSAs, meaning that they do not leave the area. Okay? We'll learn more about this as we kind of go through the process, but type 1 LSAs are generated by everybody within OSPF, but they stay within the area, and those are literally the LSAs that describe the links that the routers are attached to. Type 3 LSAs are what we call inter-area LSAs, not intra, but inter. And type 3 LSAs are what we call summary LSAs. They are a summary of all of my type 1 LSAs. So as type 1 LSAs get learned within the area, when I'm moving from one area to the next, those type 1 LSAs get converted to type 3 LSAs. Now, by default, OSPF does not summarize. So if I have 1,000 type 1 LSAs in area 0, I'm going to have 1,000 type 3 LSAs that represent those type 1 LSAs in area 1. So we'll get into the summarization aspect a little bit later on when we talk about optimizing OSPF. But the area border router, which is a router that borders multiple areas, is the router that's responsible for generating those type 3 LSAs. They're called summary LSAs because they represent, or they're supposed to represent, a summary of all of the type 1 LSAs that might exist in a particular area. All right? Gets a little bit confusing, right? Because we've got to talk about type 2 LSAs, which are network LSAs, and they describe multi-access networks. Type 4 LSAs are ASB external LSAs, and they describe how to reach an ASBR, which is a router that does redistribution into OSPF. Type 5 LSAs are external LSAs, and they describe external networks that are actually being redistributed, and that's those type 5 LSAs are also generated by ASPRs. Type 7 LSAs are very similar to type 5. They're external routes, but they're external routes with an ASPR that's attached to a special area type. So it would be like a not so stubby area or a totally not so stubby area. So a lot of detail with this protocol. And again, I don't expect, based on what I just said, that you guys would pick up on all that. It's kind of a process we go through to learn kind of the intricacies of the protocol, if you will. Okay? And that's why a lot of people will tend to classify OSPF as a very complex routing protocol, because there are a lot of ways to configure the protocol and a lot of ways to kind of set up the protocol and optimize the protocol and so on. All right. All right. So what we're seeing in this diagram here is a representation of a pretty typical kind of hierarchical design in OSPF. Again, you can choose to implement OSPF as a single topology and a single flat network, meaning that you would just simply put all of the routers and all the links in a single area, but you're going to lose a lot of the scalability functions that you have with OSPF, right? So for example, router A, we'll just kind of go from the top and work our way down here. The external routing domain, that could be EIGRP, it could be BGP, it could be static routes, it could be some other routing process, an independent router from OSPF. And router A in this case is taking routes from that external routing domain and it's redistributing those routes into OSPF. That makes that router an autonomous system boundary router, okay? So router A is what we call an ASBR. Now always, not always, but 99% of the time when somebody documents an ASBR in a topology, they always put it in the backbone. But ASBRs can exist anywhere in the topology. It doesn't have to be attached directly to the backbone area. There are some restrictions, right? An ASBR cannot be attached to a stubby area or a totally stubby area, but it can be attached to a normal area, it can be attached to the backbone area, and it can be attached to a not so stubby area and a totally not so stubby area. Those are the exceptions to the rule, I guess, from a special area type perspective. But the whole point of an ASBR is to take external routes from an external routing process and through the redistribution process, inject those routes into OSPF. Those come in as OSPF external routes. And it depends on what type of ASBR it is. If it's an ASBR that's attached to a normal area, not a special area, those routes would come in as like OE1 or OE2 routes. OSPF external type 1 or OSPF external type 2. We'll talk about the difference between OE1 and OE2 a little bit later on. It has to do with how the seed metric is applied and how the seed metric is incremented as you go through the topology. All right. If you have an ASBR that is attached to a special area type, and there are only two, a not so stubby area and a totally not so stubby area, then that would be what we call an external NSSA route. So it would show up in the routing table as an ON1 or an ON2 route. But what do those external routes represent? Those external routes represent the external prefixes that are being redistributed. All right, and again, it's very, very complex, right? When I do my CCIE mentorship program and I'm teaching people about OSPF and CCIE, here I'll give you an example here. Let me pull up my CCIE files here, just to give you an idea of the protocol and how complex it is. The OSPF discussion, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 different 2-hour recordings on OSPF, right? So what we're doing in this class is very, very high level as to what you can actually discuss when you're talking about OSPF. It is a very, very complex routing protocol. All right. Hopefully we'll see you guys in one of those programs pretty soon. It's like a 6 to 9 month program where we just, it's all online, and we do about 6 hours a week, 2 to 3 sessions a week, and just get into the nitty gritty of everything. But it's a lot of fun, but it takes a lot of time. All right. Now you can see here that the autonomous system is basically the entire OSPF system. We don't use an autonomous system number to describe that system. There's no, not like EIGRP where I say router EIGRP1 or router EIGRP100. In OSPF, we do say router OSPF, and we do provide a number, but that number is just simply a locally significant process ID that allows us to identify the OSPF process on the router locally. All of the OSPF routers are kind of assumed to be in the same autonomous system regardless of whatever the process ID might be. So the process ID for router A might be different than B, than C, than D, and so on. When you're running a multi-area design, as we see documented here, you have to have an area 0. Area 0 is the area that allows us to interconnect all of the other areas in the topology. So we call this the backbone for that reason. It allows us to identify how all of the other non-backbone areas get interconnected. Does that make sense? So area 0, there's a couple of restrictions for area 0. Number 1, it has to be contiguous. In other words, you cannot have multiple area 0s separated by other areas. It has to be a contiguous area 0. Number 2, generally speaking, we don't have clients in the backbone. We could. There's certainly nothing, there's no restriction on having clients in area 0. We could potentially have users and subnets and whatnot in area 0. But usually area 0 is designed to be our transit area. That's the area that allows us to interconnect all of our other functional areas. A router that has all of its interfaces in area 0 is called a backbone router. And by the way, you guys probably saw this in the implementation. You don't put routers into an area, you put interfaces into an area. Okay, so these 3 interfaces here would be configured in area 0 through their network statement, or by implementing OSPF directly on the interface. That backbone router is it's defined as a backbone router because it has all of its interfaces in the backbone. Now, what about routers C, D, and E? Routers C, D, and E are what we call area border routers. Area border routers. They are defined as area border routers because they do have at least one interface in the backbone and one interface that's in a non-backbone area. And the purpose of an area border router is to provide a summarization boundary. So let's say I have 1,000 type 1 LSAs that exist in the backbone here. Okay? Those type 1 LSAs are intra-area LSAs. They're link state LSAs that describe the links that the routers are connected to. When those type 1 LSAs hit the area border router, this ABR converts those type 1 LSAs to type 3 LSAs, which are called summary LSAs, because the point of a type 3 LSA is to take those contiguous range of type 1 LSAs and make them type 3 LSAs. Does that make sense? So I take my 1,000 type 1 LSAs and I summarize them as maybe 1 or 2 or 3 type 3 LSAs. Does that make sense? So that is the purpose of an area border router. And by the way, the ABR is the only place that you can actually do summarization. You cannot summarize routes on router B. You cannot summarize routes on router F or G or H. You can summarize on router A. Router A is an autonomous system boundary router, so you can summarize external routes on router A if you want. But that's the restriction, and we talked about that in our EIGRP discussion, that EIGRP allows you to summarize anywhere in the topology. So you can kind of just apply arbitrary summary statements on interfaces anywhere in the EIGRP topology. But in OSPF, you can only summarize on the area border routers or the autonomous system boundary routers. So you have to be very, very specific in your design by placing contiguous subnets in the backbone, or contiguous subnets in area 1, or contiguous subnets in area 2, so that you can apply the appropriate summarization on the area border routers. And that's really kind of the whole point of having this hierarchical design, is to increase the scalability of the protocol by having a planned out hierarchy of addresses that allows you to apply the summarization appropriately. Okay? Can a router be, an area border router be a member of more than 2 areas? Absolutely. Router C here could actually have a connection into area 2 as well as area 1, as long as it has at least one interface that's participating in area 0. That's the most important part, right? That means it is considered a backbone router because it is participating in the backbone. You cannot have direct connections between area 1 and area 2. We have to go through a router that's connected to the backbone. Now, if I wanted to communicate from area 1 to area 2, it does not mean that traffic has to go into a router that is completely in the backbone, right? If router C had a connection over to area 2, as well as this connection to area 1, we could simply communicate between area 1 and area 2 through router C because it is a member of the backbone. Does that make sense? So as long as the router's, the area border router has at least one interface in the backbone, it can act as a transit router from one area to the other. So you can see that OSPF has some very, very specific design requirements when you're implementing the protocol. All right, now router F, router G, router H, these are all considered to be kind of what we call normal routers or non-backbone routers because they have all of their interfaces in a single non-backbone area. All right. So an area is a grouping of routers that share a common, kind of common database, if you will. We'll get into some more of the design requirements and some of the design limitations, or at least the considerations that you have to have when you're dealing with OSPF as we get into some of the more advanced sections here. All right, any questions before we move on? Because I know I gave you guys a lot of information, a lot more information than what we saw on the slide here, but I just want to make sure that, and I'll be repeating myself quite a bit actually, because you know that's the one of the best ways to learn OSPF is just kind of hear the stuff over and over again, and of course implement it and play around with it. All right, now it says here multi-area design is more effective because the network is segmented to limit the propagation of LSAs within the area. It is especially useful for large networks. That is true to an extent, and this is a really important concept. OSPF, like I said, summarizes on these area border routers, but it does not do it automatically. So unless I configure summaries with the area range command, if I had 1,000 or 2,000 or 3,000 type 1 LSAs in the backbone, I would have 1,000 or 2,000 or 3,000 type 3 LSAs in the other areas that represent those type 1 LSAs in the backbone. So yes, having a multi-area design gives you the option of creating summaries and optimizing the overall structure of the database by implementing summaries, but it is not something that happens automatically. It's something that you have to configure as an administrator. So that's a really important concept. Everybody kind of describes the multi-area design as a highly efficient design that provides for scalability and whatnot, but it doesn't happen automatically. It's something that you have to implement as a network engineer. Which of the following statements are correct concerning the autonomous system in OSPF? An autonomous system consists of a collection of networks under separate administration that share common routing strategy. An AS, which is sometimes called a domain, can be logically subdivided into multiple areas. I'm reticent to say that that's the correct answer because they used under a separate administration. Autonomous systems are a collection of networks under common administration, not separate administration. So that wouldn't be the correct answer. An autonomous system consists of a collection of networks under common administration that share a common routing strategy. An AS, which is sometimes called the domain, can be logically subdivided into multiple areas. So that would definitely be the appropriate answer. Let's see what the other ones are just to make sure there's not a better one. An autonomous system consists of a collection of networks under a common administration that share a common routing strategy. An AS, which is sometimes called an area, can be logically divided into multiple ASs. No, that's not correct. Areas are the subdivisions that we create. So that's not. As I was saying, the areas are the actual subdivisions that we're creating, right? The domain is the blue box, and the areas are the subdivisions of that domain, right? The last answer, an autonomous system consists of a collection of networks under common administration, so that's true. An AS, which is sometimes called an ASBR, can be divided. No, an ASBR is just simply a router that takes external routes and puts them into OSPF. So that's a specific function of a device in OSPF. That's what we call an autonomous system boundary router. So definitely B is the right answer in this particular case. Okay? So what is the OSPF process? Just like we talked about with EIGRP, 3 major components to the protocol, right? We have the routing protocol messages that we use. In EIGRP, it was hello, update, query, reply, and acknowledgement. There was also a stuck and active query, a stuck and active reply, and a request. In OSPF, hello, link state advertisement, link state request, database descriptor, and link state acknowledgement. So very similar to EIGRP in that we have 5 major message types that OSPF uses to disseminate information. What was the second thing that we talked about? We talked about the data structures, right? The data structures. In EIGRP, it was the adjacency database or the neighbor table, the topology database, and the routing table. In OSPF, we have a neighbor table. We have a topology database, which is called the link state database, and we have a routing table. So again, the natural progression to verification and troubleshooting is to make sure that I have neighbors first, because the neighbors are who I'm learning information from. And then that goes into my topology database. And then I run my algorithm, which is the third major component that we talked about. I run my algorithm against that database to extract the routes that I'm going to use. And that goes into my global RIB, my global routing information base. Okay? So just like EIGRP, we have these 3 things that we concern ourselves with. What are the routing protocol messages that we use to communicate? What are the data structures that we use to compile the information? And then finally, what is the algorithm that we use to make decisions? In OSPF, it's Dijkstra's algorithm, or what we call the shortest path first algorithm. In EIGRP, it's dual, the diffuse update algorithm. So we have lots of kind of differences between the protocol, but we also have a lot of similarities in the overall structure or architecture. Now what we're looking at in this particular diagram is just a basic adjacency between router 1 and router 2. A couple of different things here, right? First of all, we're establishing this adjacency over an Ethernet connection. And that network type is called a broadcast network type. A broadcast network type is any network that can have more than 2 hosts connected. Yes, it's a point-to-point link, but it is an Ethernet link, which means if we had a switch in between, we could have 5 or 6 or 7 different hosts connected on that network. So because it is a broadcast network, we're sending and receiving hello packets every 10 seconds, and we're able to establish an adjacency. The timers are automatically going to be determined based on the fact that it's a broadcast network. On the left side, we specified that we're enabling the OSPF routing process by typing router OSPF 1. On the right side, router OSPF 10. Doesn't matter. These are not autonomous system numbers. These are locally significant process IDs. All right? So unlike EIGRP, where that number has to match, in OSPF, that number is locally significant, which means that you could potentially run multiple processes of OSPF on the same router. And you might do that if you're like kind of bridging 2 different OSPF domains together or whatnot. It's not very common, but you could do that. The point is that the process ID is locally significant, and it does not have to match. Now, just because I put in router OSPF does not mean that the routers are going to automatically form an adjacency. Just like with EIGRP, and just like with RIP, I have to enable the protocol on the interfaces in order for them to start generating hello packets and sending information back and forth on the interface. With OSPF, though, we have a couple of options. We can put in network statements to include the 10.1.1.0 subnet under the routing process, or we can go directly to the interface and we can enable the OSPF process directly on the interface. Just putting in router OSPF, though, just to be clear, is not going to start the routing process. Okay. Let's see here. So this is a diagram in which they're describing that we're running multiple routing processes on a router. Like I said, you can have multiple OSPF processes running on the router. In this case, router 1 is connected to 2 different kind of administrative domains, if you will. Maybe OSPF AS Group A is one company, and OSPF AS Group B is another company. And router 1 is acting as a redistribution node, or a router that's going to redistribute routes from one group to the other. And that's certainly entirely possible. We would hopefully get more into a redistribution when we get into the advanced routing section over the next week or so. All right. It is possible, like I said, to have multiple instances running. That's what this is describing. But it would require, by the way, redistribution. In EIGRP, if you have multiple autonomous systems on a router, redistribution takes place automatically. In OSPF, it does not. You would actually have to set up some redistribution commands. Now, let's talk about the router ID. That's what they're mentioning in this particular case. The router ID plays a huge role in OSPF, and it has to be unique throughout the entire autonomous system, not just within the area, but within the entire autonomous system. We have to have a unique router ID. The router ID is established the same way it is in EIGRP, which is the same way it is in OSPF, the same way it is in BGP. You manually configure the router ID. That's your first choice. And if you manually configure router ID, it takes precedence over every other option. If you do not manually configure router ID, then the router ID is selected based on the highest active IP address on your loopback interfaces. So if you have 10 different loopback interfaces, you pick out whichever one has the highest physical IP address. That becomes your router ID. So the router ID is actually written in a dotted decimal format. But it does not have to be an IP address. You could actually set the router ID as 0.0.0.1 if you wanted to. Or you could set the router ID to 1.0.1.0. Those are not valid IP addresses, but they do follow the dotted decimal format the 32-bit dotted decimal format, which is required for a router ID. If you don't have any loopback interfaces, certainly you're going to have physical interfaces, right? I mean, a router without physical interfaces isn't a router because you can't route packets from one subnet to another. So if you don't have the router ID manually configured, and if you don't have any loopback interfaces, then the router ID is going to be selected based on the highest active physical IP. All right, so when I say highest, I mean literally 10 is higher than 1. So 10.10.10.10 would be selected as a router ID over 1.1.1.1. And conversely, 192 would be selected over a 10 address, right? It does not have to be an interface that's participating in OSPF. It just has to be an active interface. So it has to be in the up state, and it has to be operational. If an interface is shut down, that would not be part of the process or included in part of the router ID process. But here's the most critical thing about the router ID in OSPF. As we get into kind of our more advanced discussion of the router ID, of OSPF as a protocol, you will see that every link state advertisement, every neighbor relationship, every kind of election process like the DR, BDR election process are all affected by the router ID. So the router ID is highly significant when it comes to OSPF. It plays a very, very specific role. In EIGRP, the router ID does exist, but we don't really talk about it much because it doesn't really play as much of a role in EIGRP as it does in OSPF. All right. So if I decide to manually configure the router ID, I would do this under the router OSPF process, and I would just simply say router ID, and I would put in a 32-bit dotted decimal formatted address. Okay. It says that's the best practice, right? Well, it's the best practice because you want to be able to document what the router IDs are. If you rely on interfaces, if an interface goes down, it's possible that the router ID is going to change. And if the router ID changes, then we have to reconverge, we have to resynchronize OSPF and so on. So we want the router ID to be stable, we want it to be unique, and we want it to be documented. It is a 32-bit number, so keep this in mind. If you're running IPv6 and you're not running dual stack, right? You're only running v6, you're not running v4, the router ID has to be manually configured because there's no way for it to choose a dotted decimal 32-bit address if you don't have any active dotted decimal 32-bit addresses on your router, right? So, and Cisco loves to ask that question on the test, but yeah, if you're doing dual stack, it's not a problem because you're going to have v4 and v6 addresses on your router. But if you're running v6 natively and you're not running v4, you're going to have to manually specify that router ID. Okay? You'll also notice with OSPF, and this is the thing that Philip, you were running into, you'll notice with OSPF that, and as we go through more and more of our discussion, you'll see this, once something is determined in OSPF, it pretty much stays that way, even if something changes down the line. So once my router ID is selected, let's say I used the highest IP address on a loopback to pick my router ID. And then I went and added another loopback interface that just happened to have a higher IP address. The router ID does not change because we want to make sure that the routing process is stable. I don't want to have a bunch of reconvergence events happening whenever I make a minor change in my topology. So that's why when you guys were setting the router ID in the lab exercise, you were required to clear the OSPF process because the router ID is a non-preemptive configuration. Once the router ID is set, that's what it remains, that's what it stays as until you reset the router or reset the OSPF process. All right. So it says here the router ID selection process occurs when the router OSPF command is entered by the administrator. Ideally, the command router ID quad X has been used under the OSPF process to establish the router ID explicitly. If not, we'll use the loopback. If not, we'll use the physical interface. All right, so instead of letting OSPF pick a router ID, which is based on the status of an interface, use the router ID command so that you can identify what that router ID is going to be. Okay, so we're starting to see more of the configuration here. We have a loopback interface that's configured with an address of 10.255.255.1. We have our OSPF process with process ID 1, and we're specifying the router ID as 10.255.255.1. That's a little redundant. You don't have to do that technically. The loopback would have automatically been chosen as the router ID. But they're just kind of showing you the fact that you can actually set the router ID to whatever value you want, even if it is an interface address. It doesn't really matter. All right. And they did the same thing on router 2. They set the router ID to 10.255.255.2. I mean, technically, loopback interfaces are not reliant on any kind of physical status, right? There's no cable plugged into them. So as long as the router's operational, as long as the router's running, those loopback interfaces should be in effect operational. But I would always recommend setting the router ID manually. All right, always recommend that. Sorry about that. All right, once the router ID is set, the next step would be then to go through the process of, turning on the protocol on specific interfaces. We can do that, like I said, with network statements, or we can go and do that on the interface directly. We'll see what that entails as we get into kind of more of our detailed configurations. In this diagram, we're seeing a configuration of loopback interfaces, and the router ID is being selected based on that. All right. They're really hammering that point home, I guess. So they mentioned it a couple of times. When a router needs to generate traffic, like a ping or a trace route or a telnet, the exiting interface of the device becomes the source of the traffic. Now, I'm not sure that that's even kind of relevant in this case, but I mean, that is a good point to note. Anytime a router generates traffic, and it doesn't matter if it's OSPF or EIGRP or just a connected router, anytime a router generates traffic, the source address of that traffic is always going to be whatever interface the packet goes out of. All right. That has no bearing on what we've been discussing. It's kind of a random place to put that, but in this case, that could be a physical interface. It's unlikely going to be a loopback. There are some scenarios when you could actually say, like in BGP, you can do like an update source command, or with an MGCP gateway, you can specify the source traffic for the MGCP control traffic and so on, or the source interface for the control traffic and so on. But usually it depends on what you're configuring as to how you can control that. What is the correct order for how the router ID is selected? They already answered the question for us. It's manually configured, it's the highest loopback, or it's the highest physical interface. Okay? All right. So what about the adjacency process? In OSPF, it's a lot more complex than in EIGRP. In OSPF, there are several different things that need to match. And actually, let me do this. So what I wanted to do is I wanted to get these this OSPF capture so that we could look at some of the basic message types that we have in OSPF, right? Now, remember what I said about EIGRP, right? EIGRP is encapsulated directly in IP. Well, guess what? OSPF is also encapsulated directly in IP. It's protocol number 89, all right? You'll also notice that we use a multicast address for our OSPF messages. In EIGRP, we use 224.0.0.10. In OSPF, there are actually two different multicast addresses that we use. 224.0.0.5, which is all OSPF routers, and 224.0.0.6, which is all OSPF designated routers. So if I'm sending traffic to a designated router, we might actually see one of those in here. Let's see if there is one. There should be one in here if we have a DR-BDR election. There it is, 224.0.0.6. So this is an example where routing information is being exchanged. So those are the two multicast addresses that we're going to use in OSPF. Also notice the time to live is 1. Any multicast address that starts with 224 is going to by default have a TTL of 1. These are non-routable, well-known multicast addresses. You can override that behavior potentially, and you could say, I'm going to go ahead and change that to make it routable, but most of my well-known multicast addresses, which are the ones that start with 224, are going to be link local scope. So what does this hello packet look like in OSPF? Just like in EIGRP, we have a header. Every single OSPF packet type has a header. Hellos, link state advertisements, link state requests, link state acknowledgments, etc. Just like in EIGRP, what's contained in the in the header, what version of OSPF are we running? Very similar to EIGRP. We called it an opcode in EIGRP, but we call it message type here. So this is a hello packet, which is a message type of 1. What is the size of the packet itself, which includes the header? So that's the payload as well as the header. Who is the router ID that's generating this OSPF packet? So that's something we didn't see in EIGRP. The router ID shows up everywhere. What area is this packet originating from? There's a checksum to verify the integrity of the packet itself. The authentication type that we're using. This will either be a 0, a 1, or a 2. A 0 means no authentication. A 1 means clear text authentication. And a 2 means hashed-based authentication. So like MD5 or SHA authentication. Now, if we look back at our slide here, we see a couple of boxes identified here. Authentication data, router ID, or area ID, excuse me, and router ID. Those are all components that are included in the actual packet header, the OSPF packet header. Router priority, DR, BDR address, stub area flag, neighbors, hello and dead interval, and that's it. Those are not part of the packet header, but those are part of the OSPF hello packet. So now if I look at the actual payload of this hello packet, we have that information. Here's the subnet mask, so we can compare whether we're in a common subnet. This is the hello interval, which is specified at 10 seconds. Now remember in EIGRP, in the hello packet, we didn't say what the hello interval was, we said what the dead interval was, because we didn't care about the timers in EIGRP, but in OSPF we do care about the timers. The router priority, the dead interval, again, something that we care about within OSPF. Who's the DR for the segment? Who's the backup designated router for the segment? These are quad 0 right now because they haven't been selected. And then we have a bunch of different options. We don't need to really get into all the options here, but you go into the CCIE class, you'll learn more about those options. And then we have some LLS data block information. Again, these are extended TLVs, type link value fields that allow us to carry other information about the adjacency in this particular case. We don't need to really get into these details either. So you can see that in the packet capture, these are epoch times, so they're not quite representative of specific times. as far as seconds go, because we should see a hello every 10 seconds. I guess that's about right? This is 0, this is 9, so the next one should be about 19, and the next hello should be at 29. So actually these are represented in regular time intervals, not epoch time. But we can see those hellos are being sent every 10 seconds. Now, eventually what's going to happen is, as I go through the process of establishing the adjacency, we're going to start to recognize things like who is the DR, who is the backup designated router. We'll talk about how that election process takes place, but we're moving from different states. So this would be like kind of the init state, and then we go into what we call a two-way state. Actually, we go into the init state. The two-way state is the next state. The two-way state, let me hold off on that. I'll just describe it since I have it here, but I don't want to overwhelm you guys with too much information to start with. A two-way state is where I list you in my neighbor list, and you list me in your neighbor list. So I know that this router, which is 3.3.3.3, has formed a two-way state with 1.1.1.1 and 2.2.2.2 because I see 1.1.1.1 and 2.2.2.2 listed in the neighbor list. If you go back and you look at some of the earlier hello packets, that neighbor list was blank. That neighbor list didn't exist, right? So we don't have a list of neighbors. We haven't elected a DR, BDR, which means that I'm kind of in the init state of the OSPF process. I've sent out a OSPF hello, but I haven't received a hello. That's one major difference in OSPF than, say, EIGRP. In OSPF, we go through multiple stages of an adjacency process. Whereas EIGRP, you're either a neighbor or you're not a neighbor, right? And I'm sure the book will describe this in a little bit. We'll get into that. So to form an adjacency, we send a hello packet. These are all the elements of a hello packet. Some of these variables are part of the OSPF packet header. Some of these are specific to the hello packet itself. But the hello packet is how we form the adjacency. And these red boxes simply indicate that those are values that have to match in order for us to be able to form an adjacency, which is actually interesting because the stub flag would also have to match as well. That should have a red box around it because if one router in the area is a stub, all the routers in the area have to be a stub router. So that should have a red box. But everything else doesn't necessarily have to match. All right. So we use hello packets to form the adjacency. Those hello packets are sent using 224.0.0.5. We have to agree on certain information. Oh, I see what they're saying. The asterisks, anything that has an asterisk next to it is something that has to match. I'm not sure what the red box means then, but anyway, those have to match as well. So routers have to agree on certain information in order to establish an adjacency. The hello protocol establishes and maintains neighbor relationships by ensuring bidirectional communication between neighbors, meaning that the neighbors share common values that allow them to become neighbors, and those common values we've already identified. An OSPF neighbor relationship is formed between two routers if they agree on the area ID, the hello and dead intervals, and authentication. So that must be what they're referencing in the red boxes. But the stub area flag would have to be one of those as well. There's no doubt about that. They probably just forgot to put a red box around the stub area flag. If I'm configured as a stub router in an area and you're not configured as a stub router and you're in the same area, we will not form an adjacency. There's no exception to that rule. We both have to be stubs in order to form an adjacency. All right. Each interface participates in OSPF is going to be participating in the 224.0.0.5 multicast group. If it's IPv6, it would be FF02:5. So all of the multicast addresses that we use for V4 carry over to V6. Just put an FF02 in front of it and you know what multicast address is going to be used. Okay. The router ID we've already talked about. The hello and dead intervals we kind of already talked about. By default, the dead timer is 4 times the hello interval. So on multi-access networks like Ethernet, it's going to be 10 seconds. For slower speed links, it's going to be 60 seconds. And I believe it's 60. Actually, it might be 30 now that I think about it, because the 180 keeps sticking in my mind with regard to the dead timer. So that means that the hello timer must be 30 seconds. That doesn't make sense either, because 3, 6, 9, 12, that would mean 120 for the dead timer. So that sounds about right to me, 30 and 120. But we'll see that a little bit later on, and I can confirm that. I should know that as many times as I've taught this, but sometimes I just can't remember stuff. All right, the neighbors is a list of the neighbors that I know I can establish an adjacency with. Just because I have a two-way state with a neighbor does not mean I'm going to form a full state with that neighbor. There are certain scenarios in which we maintain just a two-way state with a peer. Let's say I have 5 routers that share a common subnet. So 5 routers connected to an Ethernet segment. Those 5 routers have the potential of becoming neighbors. In that 5 network or that 5 router segment, one router is going to be elected as the DR, the designated router. We'll talk more about that in a little bit, but that DR is going to form a full adjacency with all other routers on the segment, so 4 other routers on that segment. Conversely, if I elect a BDR, the backup designated router, would do the same thing. If I'm not a DR and I'm not a BDR, which in the case 2 routers on that segment would be, actually 3 routers on that segment would be, because one router is the DR, one router is the BDR, and the other 3 routers are just what we call DR others. DR others never form a full adjacency with each other. Designated router others, meaning that they're a candidate to be a DR or BDR, but they're not because they just didn't win. Those routers form a two-way adjacency, meaning that they know they could become neighbors fully adjacent if they needed to, and they recognize that they exist because they're listed in the neighbor list in the hello packet, but they're not fully adjacent. So they're not exchanging routes directly with each other. So just because you're adjacent does not mean you're exchanging information. I just want to make that clear. A neighbor is anybody that shows up in your neighbor list within the hello packet. The area ID is how we communicate in order for us to become neighbors. In order for us to form either a two-way or a full adjacency, our area IDs have to match. Now, your interface has to be in area 0 if my interface is in area 0. Now the router priority, I guess we can talk about this. Let me go ahead and just do a quick diagram here. I'm sure we'll see this later on, but since they're mentioning it here, I just want to give you a very quick kind of rundown of this. Let me just go over to Paint. All right, so let's say I have that scenario of 5 routers. All right, this is not going to be pretty, but I recently upgraded my laptop because my old one was just dying. And I took all the guts out of my old one and put it into the new one. Just had a new motherboard with a higher, faster processor. And I lost my touchscreen capability, so I have to do this with a mouse. But let's say that all these routers are connected to a common subnet. All right? Now, if this was EIGRP, all of these routers would form an adjacency with each other. We would have basically kind of a full mesh of adjacencies between the peers. All right? In OSPF, because the database is so complex and because the amount of information that we're exchanging is quite significant, they decided not to do that with OSPF. They said, let's go ahead and elect a chief on the segment. Not in the area, not in the autonomous system, but just in this broadcast domain. And that chief is called the DR. All right? We also elect a backup DR, a backup designated router. It's not a very good color, but that's okay. We'll use that one. We also elect what's called a backup designated router that acts as the backup to the DR. The DR and the BDR form, and I'm just going to do this with the DR, just assume that the BDR does this as well, forms a full adjacency with all of the routers in the topology. Okay? So these lines represent a full adjacency, meaning that we exchange link state advertisements and updates and everything else. The BDR does the same thing, but I'm not going to draw that on here right now. So these two routers here are what we call DR others. So this is a DR other, this is a DR other, and this router here would also be a DR other. These routers only establish a two-way adjacency with each other. So they know they exist. They know they exist. They have similar properties that would allow them to go fully adjacent if necessary, but they don't go past the two-way state, the two-way adjacency state. So what happens if there's a network attached to this DR other, so network X, and that link goes away? The way that the exchange of information occurs is this router notifies the DR, and then the DR propagates that information to the rest of the routers in that multi-access network. That way we're not simply just flooding a whole bunch of LSAs all over the network and everybody's talking to everybody. We kind of have a chief that manages the synchronization of the database in that multi-access network. All right? So this is a concept that is unique to OSPF that allows us to increase the efficiency of this multi-access network. But there's an election that's taking place here, right? There has to be a way that we're choosing this DR. We don't just randomly choose it. Well, it's based on two values. It's based on interface priority, or as the tiebreaker, router ID. And the reason I'm bringing this up is because they're specifically talking about this as part of the hello packet. The interface priority is a value that you set. And when I say interface, I mean literally a priority value that is set on this interface. There's one on this interface, there's one on this interface, there's one on this interface and this interface. That priority value can be anything from 0 to 255. It's an 8-bit field. If I come into my Wireshark capture and I look at the hello packet, highlight the router priority, you can see it's a 2 hexadecimal value field, which means it's an 8-bit field. The hello interval is a 16-bit field. Subnet mask, of course, 32-bit field. Dead interval is a 32-bit field. Router ID is a 32-bit field, and so on. And then the neighbor list is consecutive 32-bit fields because it's router IDs, right? But the router priority is an 8-bit field, which means mathematically it can go from 0 to 255. So this router ID, or priority, excuse me, can be anything from 0 to 255. Now, 0 is special. 0 means you can never be elected. So if I want to ensure that maybe I've got a router on this segment that's really old, doesn't have a lot of processing power, it's slow or whatever, I would use 0 on that router to make sure that it never gets elected as the chief, because it wouldn't be able to process all the information that needs to be processed. 1 happens to be the default priority. So 1 happens to be the default value on every single OSPF interface, which means we have to rely on the router ID as the tiebreaker if we don't modify the priorities themselves. And 2 through 255 are configurable values that you can set as an administrator. All right. Now in OSPF, highest always wins. So it's either the highest priority or the highest router ID. So let's assume that all these priorities were set at their default. This guy has a router ID of 5.5.5.5. This guy has a router ID of 4.4.4.4, 3.3.3.3, 2.2.2.2, and 1.1.1.1. We can kind of see why the top left router would have become the DR for that particular segment. All right. Now, if I want to influence that election process beyond just the standard router ID, then what I would want to do is I'd want to go ahead and specify the priority on the interface. But here's one more thing that is kind of a pain in the butt when you're dealing with this type of scenario. And that is that this election process is non-preemptive. Non-preemptive. What the heck does that mean? It means that once the election takes place, the router that's elected as the DR stays the DR, even if somebody in that segment comes along with a better value. So as long as it's not zero, as long as the priority is not zero, any one of these routers could become the DR. If I happen to boot up this router first on that segment, that was the first router I turned on, it would become the DR. And even if router 5 came on, or router 4 came on, or router 3 came on afterwards, this guy would still be the DR because that election process is completely non-preemptive. All right? So even though you might go through the process of trying to establish who the DR is by setting the priority or making sure router IDs are set correctly, guess what? It doesn't guarantee that that's going to be the case. It doesn't guarantee that that router is going to be the DR for that particular segment. So we're going to see this later on in the book, by the way. I kind of went ahead a little bit. But the reason I did is because they're talking about router priority and DR, BDR in this particular case. So if I look at my capture here, I can see that on this particular router, its priority is set to 1, and its router ID is set to 1.1.1.1. So I can use that information to determine who the DR and BDR is going to be for that particular segment. All right. Now, what about a point-to-point link? Maybe down here I've got a serial connection, that's supposed to be a serial connection, and I've got router 6, right? Well, on a point-to-point link, I can't reduce the number of adjacencies that I have. There's only 2 routers on the link, so on a point-to-point link, there is no DR-BDR election, because the whole point of performing a DR-BDR election is to reduce the number of adjacencies that have to happen. I can't reduce the number of full adjacencies on a point-to-point link because there's only 2 routers. Does that make sense? So it's just, again, another kind of interesting concept that exists with OSPF that we'll see as we get into some of the more details later on. OSPF neighbor adjacencies are critical to the operation of OSPF. OSPF proceeds to the phase of exchanging the routing database, followed by the discovery of the neighbor. In other words, without the neighbor relationship, OSPF would not be able to route traffic. Well, that's true, right? And that applies to BGP, that applies to EIGRP. Unless I'm a neighbor, I'm not going to exchange information, period. So the adjacency process is the most important piece to this entire communication process. We have to form an adjacency before we can do anything else, okay? What they're also describing in this particular slide they're kind of jumping around a little bit, but is what happens if there's an MTU mismatch. In EIGRP, an MTU mismatch will cause issues, but with fragmentation and whatnot, but it won't necessarily force the adjacency to fail. In OSPF, by default, if there's an MTU mismatch between the devices, the routers will not form an adjacency. They'll keep kind of moving from what we call the extort and exchange state and kind of flapping back and forth. They'll get past the two-way state. They'll recognize each other. They know that they can form an adjacency, but they cannot move into the start, exchange, loading, and full states. Let me pull up something real quick here to kind of show you what I'm talking about. OSPF states, and pull up an image. Let's go with a large image here. So these are the states that we progress through as we establish an adjacency. The down state, the init state, the two-way state. So the two-way state, we've identified that we can form an adjacency, but we're not at the point where we're exchanging information. Then we synchronize our databases by going into the xstart state, which is where we do our master-slave election and DR, BDR election and so on. The exchange state is where we exchange database descriptor packets, which describe our database. We don't automatically just send our entire database to the peer. We only send what the peer needs to see, because again, these databases can be very, very large. They can contain a lot of information, so we don't automatically just exchange the entire database. So I tell you what I have, you tell me what you have as kind of a summary, and then I request details for stuff I don't have that you have, and you request details in the form of a link state request of stuff that I have that you don't have. And that's where the loading state comes into play. The loading state is actually where we're exchanging routing information using link state updates and link state advertisements. And then finally, we're fully converged when we move to the full state. There's only two states in this entire list that routers will stay in if the network is working correctly, and that's the two-way state or the full state. Any other state is a transitionary state in the OSPF process. All right, and I'm sure that we'll see, this is OSPF 101, so I'm sure that we're going to see later on in the book, we're going to see kind of a description of each of these states. So I don't want to try to fill everything in at once, but you know, it's, to me, there's a specific flow of learning OSPF that you need to follow. Sorry about that. So there's kind of this flow. When I teach OSPF, I kind of, there's a preferred way that I like to teach OSPF, and it's kind of a progression, if you will. They seem to be kind of jumping around a little bit here, but in any event, there are different things that would cause you to not be in the right state, and one of those things would be the DBD, in the DBD exchange, the database descriptor exchange. Let me show you that real quick. So this is a database descriptor exchange. In the hello packet, we don't see anything about MTU. So we can actually get to a two-way state just by exchanging hellos. But once I do my DBD, you'll see within the database descriptor, there is an MTU field that allows us to identify what the MTU is of that particular router. You might think, well, why is that important? It's important because if MTUs don't match, there's a potential of invalid database synchronization, meaning that the database is going to get fragmented because it's too large to fit inside of a single datagram, and OSPF thinks that it can encapsulate database information inside of a 1500 byte payload, but if the MTU is below that, we might be fragmenting that database information, and we're going to get invalid, the synchronization is not going to work. So you can override the behavior. You can say, you know what, I'm going to do an IP MTU ignore for OSPF and say, you know what, if the MTUs don't match, let's go ahead and exchange information anyway, but there is the likelihood that you're going to get corrupted information. So we would rather make sure that the MTUs match so that OSPF knows how it needs to format the database, the link state advertisements and the updates that it's sending back and forth between the peers. All right. So it says here, after the neighbor relationship is formed, whenever you read something like that, you automatically think two-way. That's when the neighbor relationship is established, is when you go into a two-way state. The database exchange will halt if the MTU values between the two neighbors are mismatched. So that exchange occurs in the XStart state. This is kind of related to a test question. You will get stuck in that XStart state essentially if there's an MTU mismatch. There's other possible reasons why you might get stuck in an XStart state, but that's the most common. Which three parameters must match between OSPF neighbors for an adjacency to form? The hello and dead intervals have to match. The area that they share has to match. And the authentication has to match. I think we hit that pretty well. So once these routers have formed an adjacency, what is the next step that takes place? All right. The next step that takes place, so like I was saying, as the routers form their adjacency, the next step is to exchange information, routing information itself. All right, and this is where we go into the XStart state, the exchange state, the loading state. Those are that's the process in which we're exchanging the actual routing information. Before that happens, though, we need to go into what we call the XStart state. And if I was to look at the XStart state in a capture or a debug, basically what's happening in the XStart state is the routers are negotiating who is going to be the chief of the process, right? Who's going to be the one that's the master of the exchange of information and the one that's the slave of the exchange of information. All right, and that's not the DR-BDR process that we're talking about. It's a little bit different than that, but the idea here is that we're just trying to negotiate who's going to be kind of in control of this exchange of information. We do that by the exchange of a DBD, a database descriptor packet. DBDs are also used for other types of things as well, but the DBD allows us to kind of negotiate the database itself. What they're describing on this slide here is the actual exchange of the routing information. So let's say Charles and I wanted to exchange information, and I have a complete database of stuff that I've collected. Maybe it's hundreds of routes or thousands of routes or whatever it might be, and Charles has a compiled database himself. It's likely, maybe not, but highly likely, that some of the information that he has, I already have, and some of the information that I have, he already has. Okay? So rather than send the entire database to the peer, which could take a lot of bandwidth and a lot of resources, I'm going to send you a summary of my database called the database descriptor packet. I'm going to send you a summary of my database. You're going to send a summary of your database, and then based on that, we are going to identify what needs to be synchronized. So out of those 1,000 routes, maybe 500 of them are common between us that we know about. So we don't need to exchange all 1,000 routes. We only need to exchange the 500 routes that we don't share, that we don't have in common. And that's where the link state requests come into play. Hey, I don't have any details for this prefix. Can you please send me the details for this prefix? And that gets exchanged to the peer in a link state update. By the way, that process is called the loading state. The loading state is where we're actually exchanging prefix information, routing information. The XStart state, we're kind of negotiating the master-slave relationship. The exchange state, we're sending a summary of our database back and forth between the clients. And then finally in the loading state, we're actually doing the loading of the database itself, the actual prefixes that we wanted to share between the peers. Does that make sense? So that's why we have kind of all of these unique steps in OSPF, because we're kind of going through different phases of negotiation. All right? We're going through the different phases of the negotiation. Okay? you have to kind of understand how that process works, because you might get stuck in a particular state, and then all of a sudden you're trying to figure out, why am I not exchanging information, or why are the DBDs failing, or how come I can't move beyond the two-way state, etc. All right. So that's what they're describing here. The routers exchange database descriptor packets or type 2 OSPF packets. A database descriptor includes information about the LSA entry headers that appear in the link state database. So if you actually go into your router and you type the command show IP OSPF database, you're actually seeing what that database descriptor looks like. If I type show IP OSPF database router or show IP OSPF database summary or whatnot, then I'm seeing the details of the database entries in that case. But if I just type show IP OSPF database, I'm seeing the summary of that database, just like I would see if I'm exchanging DBDs. All right. Now, what are the different packet types that exist in OSPF? We already talked about the hello packet, right? The hello packet allows us to form adjacencies. The database descriptor allows us to kind of give information about the database to our peer. A link state request is a packet that allows us to request routing information. Let's take a look at what that looks like in Wireshark here. Here's the DBD, right? And the DBD looks like this. So this is a database descriptor. And then we see in here, not the details. Let me see if I can pull it out here. It depends on whether or not this is a synchronization one or we're actually exchanging. Yeah, this is the initialization. So let's see if I have one that, this one's a little bit larger. So let's see if this one actually has prefix information. Yeah, here we go. Here's a type 1 LSA. Here's another type 1 LSA. Here's another type 1 LSA. Here's a type 2 LSA. So these are the actual kind of the summaries of these prefixes, saying, hey, I have some information here about some of these prefixes. Let me see if we see the actual information. Router LSA, which is a type 1 LSA, but I'm not seeing the actual information here. I'd have to kind of scan through the data here and find the right database descriptor, but you can see it doesn't actually contain routing information. But if I go down and go into this right here, a link state update, actually I should see a link state request before that. Right, here's a link state request. So in the link state request, this router is saying, hey, I saw something in your database that I don't have. Could you please provide me that information? All right. And we identify link state information in the database by something called a link state ID. Every link state advertisement has a unique link state ID. And in this case, we're identifying, hey, I need the information about this particular link state ID. So I should see a link state request in response to that, or a link state update, excuse me, that contains that information. So here's the link state update. And if I scroll down, I actually see the prefix information, right? So this is, there's actually multiple LSAs inside of this LSU. Here's the first LSA type 1. There's another LSA type 2. So a couple of them I already had, but 2 of them I didn't have. And this is the prefix information for those particular advertisements. This is the router that's advertising it. This is the number of links that are included in the advertisement. And these are the prefixes. 192.168.1.0 subnet with a metric of 10, that's the cost. 10.0.0.0 subnet /24, and so on. So you can actually, if you understand the process of how the routers exchange information, you can kind of walk through a Wireshark capture and see that whole exchange process taking place and you're able to identify how that process looks. All right. Acknowledgments, just like in EIGRP, an acknowledgment is a way for us to acknowledge the receipt of information. So if I send you a DBD, you're going to acknowledge it. If I send you a link state request, you're going to acknowledge it. If I send you a link state update, you're going to acknowledge it. All right. Now, EIGRP also uses 5 packet types, just like we saw. They're encapsulated directly inside of IP, so no TCP or UDP. And just like EIGRP, everything is encapsulated directly inside of IP. All right. What is the header format? We've already seen this multiple times, but we've got our data link layer header, which is our layer 2 header. We've got our packet header, which is our layer 3 header. Inside that packet header, there's a protocol field. Protocol 89 represents OSPF. And then in OSPF, we have our OSPF packet header, which is all of these fields with the exception of the data field. So version, type, packet length, router ID, area ID, checksum, authentication type, and authentication is a standard OSPF packet header. And every single OSPF packet is going to have that information. The data is going to be whatever field is related to the type of packet that we're actually sending. You know, whether it's a hello packet or an update or a request or whatever. All right? Does that make sense? All right. So it's a lot more complex, as I mentioned. And as you can see, there's a lot of stuff going on with this particular protocol. All right? And we're not even really scratching the surface, to be honest. We're getting into some good stuff here, but you can see how we could have quite a bit more information. So the version allows us to identify what version of OSPF we're running. Version 2 is OSPF for IPv4. Version 3 is OSPF for IPv6. The packet type would indicate whether it's a hello packet, a link state advertisement, or link state update. So if I come in here and I look at a DBD, for example, that is going to have a packet type of a message type of 2. But if I look at a link state or hello packet, that should be a message type of 1. Message type of 1. A link state request, I believe, is a 3. Yep, link state request is a 3. A link state update should be a 4. And then the acknowledgement should be a 5. And am I seeing any acknowledgements here? There's an acknowledgement. And that should have a packet type of 5. So that's what that field represents. It's just what type of packet are we encapsulating. That way, when whoever's processing the packet, they know, hey, this is a hello packet, so I'm going to process it as a hello, or this is an update, I'm going to process it as an update, and so on. The packet length is how much data is carried inside the packet itself. The router ID we talked about, the area ID we talked about. Checksum is a form of message integrity checking, verifying the integrity of the data. Authentication type. Like I said, we have 3 different authentication types in OSPF. No authentication, clear text authentication, and message digest authentication. So those would be respectively 0, 1, and 2. The authentication data, relevant to the authentication scheme. In clear text authentication, we would actually literally see the password in the packet capture. So that's clearly not a authentication method that we should use. The data field is the actual data that's being carried. Is it a hello packet? Is it a database descriptor? Is it a link state request? Is it a link state update? And so on. Okay. Which OSPF packet type contains a list of link state advertisements that should be updated and is often used in flooding? Which OSPF packet type contains a list of LSAs that should be updated and is often used in flooding? I believe that what they're describing there is a link state update. A link state update contains multiple link state advertisements. We saw that actually when we looked at the capture in Wireshark. I hesitated for a minute because I'm thinking Could it be a DBD? Are they talking about a summary of my link state advertisements? But I'm going to go with a link state update, which gets flooded throughout the area. Okay? So, what are the different LSA types? Now, this gets kind of really confusing, but once you've gone through it a couple of times, it tends to make sense. Different types of routers in OSPF generate different types of LSAs. Now, there are multiple types of LSAs. As you can see, there's 1 through 11, but there's only a handful of these that you're going to see on a regular basis. Every OSPF router generates a type 1 LSA. There's 3 things you need to know about the types of LSAs. You need to know who generates them. You need to know what they represent, what their purpose is, and you need to know what the scope of that LSA is. So I'm going to describe each of these, and I'm going to define those 3 things for each of these LSA types. Okay? Who generates it? What is its purpose, and what is the scope? When I say scope, I mean, is it flooded throughout the entire autonomous system, or does it stay within the area? So we call it intra-area or inter-area scope. Intra-area means that LSA stays within the area. Inter-area means the LSA goes from one area to the other. Okay? So what is a type 1 LSA? Type 1 LSAs are generated by all routers in OSPF. Type 1 LSAs describe the links that are attached to the router. Okay. So type 1 LSAs describe the actual links that I own, right? That's why every router in OSPF generates type 1 LSAs, because these are the LSAs that actually describe the links. They're called router LSAs. I remember that by just simply saying, well, every router in OSPF generates those LSAs. A router LSA is an LSA that describes the directly connected links on a router. The scope of a type 1 LSA is intra-area. Type 1 LSAs get generated in every area, even special area types, but they don't leave the area as type 1. Okay? So who generates type 1 LSAs? Everybody. What is the scope of a type 1 LSA? Intra-area. And what is the purpose of a type 1 LSA? To describe the links that are connected to the router. Okay? Type 2 LSAs are generated by DRs and BDRs. A type 2 LSA describes the multi-access network that the DR is responsible for managing. Okay? So a type 2 LSA describes who's attached to that multi-access network, who is the chief of that multi-access network, and so on. The scope of a type 2 LSA is intra-area. They don't leave the area. Okay? So again, who generates type 2 LSAs? The DRs and the BDRs. What is the purpose of a type 2 LSA? To describe the multi-access network that the DR is responsible for. And what is the scope? Intra-area. All right? Type 3 LSAs. Type 3 LSAs are generated by ABRs, area border routers. Now, what is the purpose of a type 3 LSA? The purpose of a type 3 LSA is to summarize type 1s into other areas. So if I have 1,000 type 1s in area 1, what's supposed to happen, if those are contiguous subnets and I've configured the area range command on the ABR, what's supposed to happen is those 1,000 type 1 LSAs are going to get summarized into a single type 3 LSA as it leaves the area. Does that make sense? That's why these are called summary LSAs, because they're supposed to represent summary routes. So who generates type 3 LSAs? The ABR. What is the purpose of a type 3 LSA? To summarize type 1s. And what is the scope of a type 3 LSA? Inter-area, meaning type 3 LSAs move from one area to the other. So for example, if router 1 had area 51 attached to it, that type 3 LSA that was originated by router 2 would go through router 1 and into area 51. And it would be processed as a type 3 LSA. So type 3 LSAs get flooded throughout the entire autonomous system. The only exception, areas that are totally stubby or totally not so stubby will not accept type 3 LSAs. Hopefully we'll get into that a little bit later on. Okay? There's only 11 of these guys, so we should be done with this in about 3 hours. All right? I'm going to skip type 4 for a second because type 4s are related directly to type 5s and type 7s. All right? So a type 5 LSA would be generated by, they don't have it, must be cut off. Let me scroll down here. Yeah, there we go. A type 5 LSA is generated by an ASBR, an Autonomous System Boundary Router. That would be a router that is redistributing into OSPF. Those type 5 LSAs describe external networks. Okay, and you can see from the arrow there that it is a inter-area LSA, meaning that it moves from one area to the next. So literally, if I'm redistributing the 10/8 subnet from the external routing domain into OSPF, I'm going to have a type 5 LSA that describes the 10/8 subnet. It describes who's originating that route, router 3, but it doesn't necessarily describe how to get to the ASBR. So the point of a type 4 LSA is to describe reachability to a an ASBR. So you'll never see type 4s unless you have type 5s. Notice who's generating that type 4. The ABR that is attached to the area that has the ASBR in it. Type 4s don't exist in area 1 because everybody in area 1 knows how to get to the ASBR through the type 1 LSAs. But when the ASBR advertises its type 1 LSAs, it sets the external flag to indicate that it is an ASBR, which then triggers the ABR, router 2, to start generating type 4 LSAs to describe to everybody else how it needs to get to that ASBR. Does that make sense? I know it's a lot of information, guys. This is something that I normally spend about 2 or 3 hours going over with lots of diagrams and whatnot. Hopefully when we get into the advanced routing piece, we'll see this again. But those are the main LSA types. Now, there is one other that I'll mention. Actually, 3 others that I'll mention. Type 7 is one that you would see kind of on a regular basis. A type 7 LSA is exactly the same as type 5. It describes external networks. It is well, it's actually technically not inter-area because type 7s get converted to type 5s at the ABR, but it does move from one area to the other, technically, the information that's contained in the LSA. But it's an ASBR that's attached to a special area. So if area 1 was not so stubby, or if area 1 was totally not so stubby, those type 5s would be type 7s in the green box, but then they would get converted to type 5s as they go through router 2. Does that make sense? So the last 2 I'll talk about are type 8 and type 9. I'm not going to get into detail, but they are LSAs that are used for IPv6. Which we'll be talking about later on. So I'll get into that a little bit later on. All right. So like I said, you're not going to remember all this stuff just from discussing it one time. My suggestion would be when you focus on learning LSA types, just focus on learning those 3 aspects. Who generates the LSA? What is the purpose of that LSA? What is its purpose? I mean, what does it describe? And what is its scope, right? Where does it go within the domain? That's a good, solid starting point for learning these different LSA types. So just a refresh real quick, I'm just going to kind of read through these bullet points. Every router generates router link advertisements within the area that they belong to. The router link advertisement describes the state of the router links in that area, and they're flooded only within the area. For all types of LSAs, there is a 20-byte LSA header. That's our standard 20-byte OSPF header. One of the fields in the LSA header is the link state ID, and the link state ID of a type 1 LSA happens to be the router ID of the router that's originating that type 1 LSA. Actually, you're going to see that most of the LSA types, the router ID is the link state ID or the link ID, but there are some exceptions to that. Okay? Type 2 LSAs, DRs, designated routers, generate network link advertisements for their multi-access networks. The network link advertisements describe the routers that are attached to that multi-access network. They're flooded within the area. The link state ID of the type 2 LSA is the actual physical IP address of the DR's interface for that particular multi-access network. So if I have a router that's the DR for a 10.0.0.0/8 subnet, and the IP address on that interface happens to be 10.0.0.1, that would be the link ID, the link state ID of that particular LSA. Now, they say they're flooded within the area, but they don't really leave the area. A lot of people will say that type 1s and 2s become type 3s, when in reality type 1s become type 3s. Type 2s don't necessarily become type 3s. Type 3 LSA, area border routers, take the information that they learn in one area, say area 1, and they summarize them into the other areas as a summary link advertisement. Again, that does not happen automatically. In order for that to happen, you would have to configure the area range command under the OSPF process to perform that summarization. The link state ID of a type 3 LSA is the destination network number, meaning the summary address. So there is another field called the advertising router, which is the router ID of the router that's generating the type 3 LSA, but the link state ID is actually just the summary address that was created. Okay? So let me skip over type 4 again. I'll go back to type 4. Type 5 AS external link advertisements, what we just simply call external LSAs, basically advertise external networks. I lost my spot there. Okay, yeah. So they're generated by the ASBRs. They describe the external routes. They get flooded everywhere except for special area types. And by the way, external LSAs never go into any special area type. It could be stubby, totally stubby, not so stubby, totally not so stubby. The type 5 LSAs never enter a special area type. Okay? The link state ID is the actual external route that is being advertised through the redistribution process. Type 4 LSAs, like I said, describe how to get to the ASBR to the rest of the network. So these are generated by the ABR on the egress of the area that contains the ASBR. The link state ID includes the router ID of the ASBR. It's a really interesting concept. In OSPF, and in my CCIE class, I kind of teach this concept. OSPF is less about routing to networks and more about routing to nodes. Much like BGP is routing to autonomous systems, in OSPF we're more concerned about routing to a node than routing to a specific network. That's why the router ID plays such a specific role in OSPF for that particular reason. Other LSA types, type 6, multicast, type 7 are basically the same as type 5, just an ASBR that's attached to a special area type. NSSA and totally NSSA to be specific. Type 8 and Type 9, link local and intra-area prefixes. So Type 8 would be your FE80 prefixes, your link local addresses, which exist in IPv6 but don't exist in IPv4. And Type 9, intra-area prefixes would be like your global prefixes and whatnot that might exist, very similar to like a Type 1 LSA. Type 11 and 10 and 11, future use. So opaque LSAs, meaning that they're not really totally defined. Certain applications of OSPF will use those, but it's not really defined specifically. All right. So kind of crazy, a lot of information, but I think you guys are pretty good. It takes a lot of time. I mean, it took me teaching this probably 10 or 15 times before I finally just kind of got it and it made sense. So don't be discouraged if this seems a little bit overwhelming. All right. And we don't need to do the question because they already answered the question for us. All right. So what is the difference between single area and multi-area OSPF? Well, single area OSPF, everybody's within a single area. So what types of LSAs could I potentially see in that type of design? 1s and 2s, that's it. I would never see Type 3s, Type 4s, Type 5s, Type 7s, maybe 8s and 9s if I'm running IPv6, but only 1s and 2s. So essentially everybody within the area is going to have an exact copy, same copy of the database. Doesn't scale well, especially if you have hundreds or thousands of routes. When I introduce a multi-area design, that's when we start to see the different LSA types. That's where summarization can occur. Again, not automatically, it's manual, but that's the whole point of kind of developing this hierarchy in OSPF, is for scalability purposes, to be able to scale the network to an appropriate size. Okay? Let's see what they say here. Single area OSPF, many LSAs are processed on every router. We have very large routing tables, mainly because we can't do summarization, right? You have the absolute potential of having very large routing tables even in a multi-area design if you don't do summarization correctly, right? And if you don't have contiguous address blocks, you can run into a situation where summarization is not even possible. So you're not going to get the benefit of scalability in that type of design, even if you have multiple areas implemented. Okay? So multi-area configuration is pretty typical with OSPF. All right. There are two types of routers that are from a configuration point of view. There's an internal router, which is a router that has all of its interfaces in a non-backbone area. There is a backbone router, which has all of its interfaces in the backbone. An autonomous system boundary router, which does redistribution from an external AS. And an ABR, which in a multi-area configuration would be required, which would be a router that connects multiple areas. So you could see potentially internal and backbone routers in a single design. Say, for example, I decided just to implement one area. I could actually make it area 1. If I'm doing single area implementations, I don't actually technically have to have an area 0. The whole purpose of area 0 is to act as a transit area between other areas. So I could use area 1 as my single area, and in that case I wouldn't necessarily have any backbone routers, but I would have all internal routers. And I could actually still attach an ASBR to that area, much like you see on area 2. If I do have a multi-area configuration, I have to have an ABR. All right? All right. We talked about all this in some of the previous slides that we saw here. I like the bullet point there. While multi-area OSPF is scalable and very powerful, you need to know what you're doing, right? Absolutely, you need to know what you're doing. Multi-area OSPF offers the following advantages. It can make the routing table smaller if you're doing summarization. Again, doesn't happen automatically. If I'm not doing summarization on my ABRs, whatever type 1 LSAs exist in one area are going to get created as type 3 LSAs in all of the other areas automatically. All right? The other benefit is if I am doing summarization, let's say, for example, if we go back to the diagram here, let's say, for example, Area 1 has 1,000 different Type 1 LSAs, and I've summarized those 1,000 contiguous address blocks into one LSA, a Type 3 that goes into Area 0. What happens if one of those 1,000 LSAs or one of those 1,000 links go down? There's reconvergence in Area 1 because the Type 1 LSAs are flooded through the area, but the summary doesn't change because the summary still summarizes the other 999 prefixes. So even though a topology change occurred in Area 1, we don't have to do any kind of reconvergence in Area 0 and Area 2 because the summary doesn't change. We'll talk more about summaries a little bit later on. Which router is located in multiple OSPF areas and maintains separate link state database for each area? That would be an area border router. That's the only router that actually connects multiple areas. An ASBR connects multiple systems, like non-OSPF to OSPF, but it doesn't connect multiple areas. Could an ASBR also be an ABR? Absolutely. You can have an ABR that connects Area 0 and Area 1 that happens to have an external link and it's doing redistribution. So the router can act as an ASBR and an ABR in that particular case. All right? All right. So the area structure, we've already kind of talked about a little bit. The whole box is the autonomous system. Area 0 has to be directly connected to the other areas. Areas cannot be connected to each other. So for example, I can't connect Area 1 to Area 2 directly. I have to go through Area 0. Area 0 has to be contiguous, meaning I can't have, say, an Area 0 here and then have another Area 0 down here. So there's a very specific structure that has to take place in order for OSPF to function correctly. There are some exceptions to the rule, right? All of my non-backbone areas technically are supposed to be directly connected to the backbone through an ABR or through multiple ABRs. And you can have multiple ABRs for redundancy, but everything should be connected to the backbone. All right? Now, that being said, what if I had a situation where Area 2, where's my mouse? Area 2 here had some other area, Area 51, connected down here. And Area 51 is what we call discontiguous or not connected to the backbone. There is a special case configuration that you can implement called a virtual link, which allows you to create, in essence, a tunnel through Area 2 to virtually attach Area 51 to Area 0. But that virtual link can only exist through one area. So you couldn't have maybe 3 or 4 areas separated from Area 0 sequentially and just create virtual links to all of them. Virtual links are only intended to be used kind of in the process of transitioning from a certain design to another design. So they're supposed to be temporary. They're not supposed to be permanent. All right, let's see what they're saying here in the chapter here. The backbone area is allows us to interconnect all of our other areas. They have to be directly connected. Yeah, we said all that. The normal areas or non-backbone areas must be connected to Area 0. Again, I mentioned this before, but it doesn't mean that Area 2, this ABR, has to send traffic into the backbone and over to another ABR to get to Area 1. I could take a link from router 5 here and in Area 1, and I could connect it to this ABR in Area 1, which would then extend this area up to this ABR. And that traffic then could flow directly between those areas going through this ABR in that fashion. But because there's a link in the backbone, this ABR technically is considered a backbone router. I guess my point is you don't have to go through a backbone router that only has interfaces in the backbone to transit from one area to the other. Okay? Let's see. OSPF has special restrictions when multiple areas are involved. One of the areas has to be area 0. All the other areas have to be connected to the backbone. The area can be identified with a decimal number or a 32-bit dotted decimal number. So I could say area 0 or I could say area quad 0. Area 14 would be area 00014. Area 300 would be 00144. We'd have to take 300 and kind of convert it to binary and then convert it back to decimal to do that. All right. So I think that makes sense. This is an example of a design where kind of our backbone, our physical backbone, which could be our WAN or it could be our MPLS network or whatever, interconnects all of our different locations. And the ABRs act as kind of the boundary between our branch offices and our corporate office, or maybe a distribution node within our campus or whatever. It depends on what your overall topology looks like. Remember, the whole point of having a multi-area design is to be able to scale OSPF to a certain size through the use of the limiting of LSA flooding and summarization, right? So there isn't a hard, fast rule as to where the ABR should be, how the areas should be divided up. It really depends on your IP addressing scheme, your physical layer connectivity, your data flow, etc. will depend on how you decide what's going to be an ASBR, what's going to be an ABR, what's going to be a backbone router, and so on. All right? And I'm not going to read this description because it's just one example of what you could see potentially. All right? Let's see. An ABR connects multiple areas together. Normally, this configuration is used to connect area 0 to a non-backbone area. And OSPF ABR plays a very important role. We've already talked about this, right? It is the router that brings all of the efficiency into OSPF. And how does it do that? Summarizing. All right? The second bullet point there, it becomes the primary point for address summarization. Now, we will talk about special area types as well. Stub areas, totally stubby areas, not so stubby areas, totally not so stubby areas. That is a function of a configuration that has to occur on the ABR as well as on all the routers that are part of the special area. But the ABR is kind of the focal point of that special area type configuration as well, because the ABR is kind of like the traffic cop. If I have a special area type, the ABR allows me to define what's allowed to come in and into the area. We don't really limit what leaves the area as far as routing advertisements, but with special area types, we limit what can come into an area. Say, for example, a stub area. Stub area means that everything can leave the area. Any routes that exist, those can be advertised as type 3s going out of the area, but only type 3s are allowed to come in. Type 5s are not allowed to come in, which means type 4s are not allowed to come in. Totally stubby area means that the ABR is going to block not only the type 5s and type 4s, but also the type 3s. So the only thing that gets injected into the area is a default route so that we can still have reachability, and all of the internal LSAs that would exist anyway, the type 1s and type 2s. So we'll get into the special area types. Not so stubby is basically the same as a stub. The only difference is you can have an ASBR and type 7s. And totally not so stubby is the same as a total stub. Again, the only difference is you can have an ASBR with type 7s. In a stub area and a totally stubby area, you're not allowed to have an ASBR. Means you're not allowed to have an external router connected to that area. But again, all of this is really controlled by the configuration of the area border router to start with, and then the configuration of the remaining routers in the area. Okay? Any router that does redistribution, whether it's a default route, we see here default information originate, that's kind of a redistribution process where we take a static default route or some other default route that exists on the router and we redistribute it into OSPF, that becomes an ASBR. So again, you are restricted as to where you can attach those ASBRs in certain cases. All right. Which two describe the backbone area in OSPF? An optional area that is designated by the administrator. That could be true, by the way, if you're doing single area OSPF. You don't have to have a backbone. Area 0 for sure, not area 1. Interconnects with all the other areas is true, because that's how we communicate from one area to the other. Only connects with other area 0 routers is not true. The whole point of area 0 is to talk to other area 0s. I mean, to talk to other areas. I just said the one thing that I said wasn't true. Yeah, area 1 wants to talk to area 2. It's going to have to go through area 0. All right? So, so the last thing we're going to talk about before we get into the discovery is what are the different network types. In EIGRP, we didn't care about network type. We don't care if it's frame relay, if it's Ethernet, if it's point-to-point HDLC or PPP connection. It didn't really matter. EIGRP pretty much treats every network interface type the same way. Now, the network type in OSPF is typically going to be defined by the encapsulation protocol that is running on that interface. So if it's Ethernet, OSPF is going to assume it's a broadcast network. If it is PPP or HDLC, OSPF is going to assume that it's a point-to-point circuit. If it's frame relay or ATM, OSPF is going to assume that it's non-broadcast multi-access. And if it's a loopback, it's going to assume it's a loopback. And OSPF treats every single one of these different network types differently. You can override that behavior. You can make a point-to-point link point-to-multipoint. You can make a point-to-point link broadcast. You can trick OSPF into thinking it's a different type of network. But the idea was that OSPF was going to behave differently on, say, a point-to-point link than a broadcast link. For example, I know I would do a DR-BDR election on a multi-access network like Ethernet, but I'm not going to do a DR-BDR election on a point-to-point circuit. There's no point because there's only 2 routers that can communicate. So OSPF defines these 6 network types, and it automatically discovers these network types. You can see how it was discovered by running the show IP OSPF interface command. But you have to be careful because frame relay is probably one of the ones that we run into the problem with the most. Frame relay does support broadcasting if the PVCs that are set up allow broadcast traffic, and that's up to the service provider for that to happen. But OSPF is automatically going to assume that frame relay is non-broadcast. Well, guess what? Non-broadcast also means non-multicast. And in order for us to establish an adjacency between OSPF peers, we have to use multicast, don't we? I mean, that's the whole point. Hello packets are sent using multicast. So any network that is considered to be non-broadcast, automatic neighbor discovery would not be allowed. OSPF would basically assume that neighbors would have to be manually configured so we could do unicast hellos instead of multicast hellos. So when you're configuring OSPF, you have to pay close attention to how OSPF is interpreting the circuits, because frame relay can support broadcasting and can support multicast. It's just a matter of whether or not the service provider will allow that traffic. So you may decide to change the network type on a frame relay circuit from NBMA to point-to-multipoint, right? There's two things that I teach people about this particular table here, because the Cisco loves to ask about this kind of stuff on the test. Non-broadcast means no automatic neighbor discovery. Any network type that has the word non-broadcast in it, no automatic neighbor discovery. Any network type that does not have the word non-broadcast means automatic neighbor discovery is allowed. Okay? Point to anything. Point to point, point to multipoint, point to multipoint non-broadcast, no DR BDR election. Point to anything, no DR BDR election. Now, in the case of point to multipoint, you actually could do a DR BDR election. The multipoint side would be the DR, and the point sides would be DR others, or other routers. But by default, if OSPF sees a point to anything, it's going to assume that there is no DR BDR election on that circuit. So that's two of the things that you typically have to understand for the exam. But the most critical piece is the hello intervals, the default hello intervals, because it's possible that you could have a frame relay network that is a hub and spoke design where the spokes are point to point and the hub is point to multipoint. Notice the timers are different. For the point to point side, the hello timer would be 10 seconds, and the point to multipoint side, the hello timer would be 30 seconds, which means we wouldn't form an adjacency. All right? Thankfully, you can do one of two things. You can either just simply change the network type under the interface by using the IP OSPF network type command, or you could change the timers under the interface by using the hello interval and dead interval configuration commands. All right. I'm not going to read each of these bullet points because I've kind of already described what each of these bullet points represent. Right. Point to point is literally two routers that are connected back to back using some sort of point to point protocol. You can actually, for example, to reduce the amount of exchanges that the routers have to take, let's say that I have a back-to-back Ethernet connection with a /30 prefix, right? So it's literally configured as a point-to-point circuit, even though OSPF would assume it's broadcast because it's Ethernet. Well, I don't want to do a DR-BDR election on that circuit. There's one side's going to be the DR, the other side's going to be the BDR. They're going to have to form a full adjacency. So I don't have to do a master-slave negotiation. So I could change that network type to point-to-point. Even though it is Ethernet, which would be considered broadcast, I can tell OSPF, treat this like a point-to-point circuit. So that's how we would be able to kind of add efficiency to OSPF. All right? Unique to OSPF. This whole concept is completely unique to OSPF because it is, we don't see this in EIGRP, we don't see it in ISIS, we certainly don't see it in RIP. RIP is a horrible protocol. But just pay attention. Pay attention to the network types because the timers are important. Whether automatic neighbor discovery is allowed or not is also important. So here and here, no automatic neighbor discovery, which means, guess what? You have to statically define the neighbors using the neighbor command. It'll still work, but we're going to be converting our hello packets from multicast to unicast. So by specifying the specific IP address of the peer, of the neighbor. All right. Let's see. Which two OSPF over frame relay modes elect a DR? Well, anything that's not point to something, right? Point to anything, no DR, BDR election. So broadcast, non-broadcast, and there is no such thing as multipoint to multipoint. So in broadcast and non-broadcast, we would elect a DR and a BDR, but point-to-point and point-to-multipoint, we would not. Okay? By the way, non-broadcast is X25, frame relay, ATM. These are examples of networks that traditionally didn't support broadcasting, even though you could get them to do broadcasting if the service provider was going to allow it. All right? All right, guys, welcome. We're going to go ahead and get into our next discovery. In this case, it's going to be discovery number 7, implementing multi-area OSPF. Now, as we go through this discovery, we're going to learn how to configure, how to establish OSPF neighbor relationships in a multi-area environment. We're going to take a look at what is the impact of the interface MTU and the OSPF hello and dead timer parameters when we're trying to establish these OSPF neighbor relationships, and how does it affect the formation of those neighbor relationships. We're also going to take a look at how the DR and BDR elections are going to take place. We talked about this, of course, in the lecture portion of the course, or the section anyway. We're going to take a look at this as a practical application. And how do we control that? How do we control who's elected and what role they're going to take? We have access to basically 5 routers in this particular topology, router 1 all the way through router 5. Router 4 and router 5 are actually already pre-configured. We're going to go ahead and configure R1, R2, and R3. Now, if you look at the diagram, R1, R4, and R5 are connected to a common multi-access segment. That means that there's going to be some sort of DR, BDR election on this particular segment. Also, R1 and R2 are connected. They're going to be connected over a point-to-point serial link. And then R1 and R3 are going to be connected over an Ethernet WAN link. So our tasks in this particular discovery are, number 1, how do we enable OSPF on R1, R2, and R3? How do we verify that OSPF functionality? How do we verify the DR and the BDR election process? We're also going to take a look at the MTU-related OSPF issues, specifically when it relates, as it relates to, an MTU mismatch on a link. And then we're going to take a look at, finally in this discovery, how do we modify the OSPF timers? What is the effect of modifying those timers, and so on? All right. All these routers already have their basic configuration in place, all the IP addressing, host names, etc. Like I said already, R4 and R5 are configured with OSPF. All right, so the first task, we're going to go ahead and enable OSPF on R1, R2, and R3. We'll start by going into R1 and take a look at, I like to do a quick show IP protocols, make sure I'm not running any other routing protocols or any other routing process, just to make sure that administrative distance is not going to have an effect on my configuration. I can also do a show run section OSPF to see if I have any OSPF configuration. So I'm going to type configure terminal, and I'm going to go into router OSPF 1. Now if I do a show IP route pipe include connected, I can see what interfaces are connected to this particular router. I'm going to go ahead and enable OSPF on the 145 network, which is Ethernet 1.1. That is going to be in area 0. And I should get adjacencies with router 4 and router 5 in that particular case. And then I should also enable OSPF on the 12.0 subnet. That should be in area 1. And I should enable OSPF on the 13.0 subnet. That should be in area 2. So I'm just going to use my network statements. We could, if we wanted to, enable OSPF explicitly on the interfaces, but we're going to make sure that we're keeping kind of a consistent configuration in this case. And we'll go ahead and put that network into area 0. Now I could, in this particular case, if I wanted to, simply reference the actual physical IP address on that interface. If I come in here and I do look at my local interfaces, I could see that .1 is that interface. So I could have used a quad 0 wildcard with a 45.1 here, and ultimately the end result would be the same. I'm going to go ahead and do a network for 172.16, 12.0 as well, 0.0.0.3. We're going to go ahead and put that guy into area 1. And then finally 172.16.13.0, 0.0.0.3. And we're going to go ahead and put that interface in area 2. All right. So it doesn't really matter how you implement the network statements. The network statements themselves don't technically define what gets advertised. It's what's configured on the physical interfaces is what's going to define what gets advertised, okay? Think of the network statements as kind of a light switch. I'm turning on or turning off the protocol on any interfaces that fall within the scope of that particular network statement. So to enable the OSPF process on the router, we use the router OSPF process ID command. The process ID numbers on different sides of the link over where the OSPF routers form their neighbor relationship, they don't have to match. This is not like an autonomous system number like we saw with EIGRP. Now, it does kind of make sense to go ahead and have them match, right? To be consistent throughout your configuration, particularly for troubleshooting. The process ID itself is really just an internal reference number or an ID to internally identify the parameters for a specific OSPF routing process, and it only has local significance to the router. We could specify actually multiple OSPF routing processes on the router at the same time if we wanted that router to participate in multiple OSPF sessions at the same time. Now, there are actually multiple ways that we can enable OSPF. We can do it on the interface, right? So we go into the interface and we define how OSPF is going to run on the interface. Let's say, for example, in this case, Ethernet 1.1, right, which is the 145 subnet. If you look at our configuration, we put that into area 0, right? And we're running OSPF process 1. So I could go into Ethernet 1.1 and I could say IP OSPF 1 area 0. That would basically enable the process on the interface. Now, if you specify the process on the interface, and this area ID happens to be different than the area ID that you may have specified in the network statement, the interface-specific configuration will always take precedence over a network-based configuration. In addition, if I had multiple network statements that overlapped or conflicted with each other, the more specific network statement, in other words, the one that has the most significant bits that match, is the one that's going to ultimately be used. All right, so you can have overlapping network statements. It's not generally recommended, but you could just note that the most specific one is what's going to be used. All right. So, like I said, there are lots and lots of different ways to effectively change or get OSPF to join a particular network. An interface to join a particular OSPF process. And again, how you decide to do it is entirely up to you. Just understand the impact of what those network statements do or what the specific implementation on the interface does. All right. Now, Cisco iOS software sequentially evaluates the IP address wildcard mask pair that we specify in that network statement for each of the interfaces. It takes a logical OR operation between the wildcard mask argument and the interface's primary IP address. Not the secondary IPs, but the primary IP address. Secondly, it does a logical OR operation between the wildcard mask and the IP address argument in the network command. All right, we compare the two resulting values. If they match, OSPF is basically enabled on that interface. If they don't match, OSPF is not going to be enabled on that interface. Here's the bottom line. Zeros in the mask mean I care, binary zeros, not decimal zeros. Ones in the mask, so the last two bits in this particular case are 1. Ones in the mask mean I don't care. So the first 30, in this case 30 bits of this address, the first 30 bits of this address have to match the interface in order for that interface to be participating in OSPF. Okay? Now, the area ID itself is actually technically a 32-bit number. It can either be represented as an individual integer or it can be represented in a dotted decimal format. If you decide to represent it in a dotted decimal format, the area ID does not have to represent an IP address. It's just a specific way of writing that same number in the integer format. So for example, if it's area 0, it would be 0.0.0.0. If it's area 1, we would say area 0.0.0.1, and so on. Now, for us to be able to establish an OSPF full adjacency, the neighbors have to be in the same area. There's some other things that have to match as well, right? We have to have the same authentication. We have to have the same hello and dead intervals. We have to have the same MTU. We have to have the same stub area flag if we're using stub areas, and so on. So there's several different things that have to match in order for those routers to form an adjacency. All right. Also, interfaces themselves can only be attached to a single area. If the IP address ranges specified in the different areas overlap, we're going to use that network command that's going to have a more specific match, all right, and we're going to ignore the rest of them, all right? So just pay close attention. Make sure you don't have any overlapping configurations. You just want to avoid any potential conflict, all right? So we did get 2 console messages here. We got a syslog message here that says that the process ID is started. The neighbor 4.4.4.4 is established. Neighbor 5.5.5.5 is established. So we went from loading to full. You know, we transitioned through the down, the init, the two-way, the extart, the exchange, the loading, and the full states. All right, so now we're going to go ahead and do this on router 2 and router 3. I'll go into router 2, config T, router OSPF 1. Do show IP protocols real quick just to make sure. Looks like actually router 2 is already running OSPF. Do show run pipe section OSPF. Let's see if it's, yeah, just the process has been started. So we don't actually technically have any network statements. So we'll go ahead and, well, actually, you know what? It was started here because I put it in. So I should have run this show IP protocol command prior to that. But in any event, let's go ahead and put in our network statements. Do show IP route pipe include connected. So we have 2 networks. 12.0 should be in area 1, and the 2.0 subnet should also be in area 1. If we go back to our topology diagram, this is router 2. So the loopback is going to go in area 1, and this serial link is going to go into area 1. All right. So we could actually put in kind of a really generic network statement. I'm going to be consistent with my configuration. That's the thing too, right? For troubleshooting purposes, you always want to maintain some sort of consistent configuration. So if you decide that you're going to implement OSPF a certain way on one router, make sure that you implement OSPF the same way on all the other routers so that when you're going through the process of troubleshooting and verifying operations, that you're not going to be concerned with whether or not there's going to be an issue troubleshooting. Maybe something just isn't consistently configured. So you think something is configured a certain way and it's not, and you end up kind of running around in circles trying to figure that out. All right. So config T, router OSPF 1. And actually, yeah, we're using process ID 1. It doesn't really matter. Like I said, you could use a different process number, but we'll go ahead and stick with 1. Let me do a show IP route, include connected here. So the 13.0 subnet is going to go into area 2, and then the loopback interface is going to go into area 2 as well. Now, just to make a point here, and this kind of goes against what I just said, but I could technically come in here and go 172.16, 13.2, 0.0.0.0, area 2, and I could even go into interface loopback 0 and say IP OSPF 1, area 2. So you can kind of mix and match these configurations. Like I said, it's not recommended because, again, troubleshooting becomes a little bit more challenging if you don't have a consistent baseline configuration that you're trying to measure against on each of the different platforms. Because we use the quad 0 wildcard mask, that means only the interface with that specific IP address listed is going to be enabled for OSPF. And like I said, another method that you can use for OSPF is to simply enable the process directly on the interface using that specific OSPF 1 area 2 command. All right, then you can forgo the use of the network statement. You know, that's an okay process. The only problem with using that particular method is now you're going to have kind of a OSPF configurations that are mixed throughout the entire configuration, as opposed to having everything under one nice, concise configuration. Now, the other thing that we want to do is we want to go ahead and establish our router IDs. If I do a show IP protocols, I can see what the router ID is for the particular router. You'll notice in this case it's 172.16.145.1, right? That happens to be, in our particular case, do show IP interface brief. That happens to be the address of the Ethernet interface. We don't have a loopback interface on this router, or it would have been chosen, that address would have been chosen. So in this case, it's the 145.1 address, which happens to be the highest physical IP address on our physical interface. But we want these router IDs to be stable, to be consistent. So again, we want to kind of, as a best practice standard, set these router IDs manually. So I'm going to go into router OSPF 1, and I'm going to say router ID 1.1.1.1. Now, if I do a show IP protocols, you'll notice that that router ID did not change, and it says here you need to reload the router or use the clear IP OSPF process command to reset that router ID. All right. Now, keep in mind you're going to lose your adjacencies in this particular case, but now if I do a show IP protocols, I can see that the router ID has become 1.1.1.1. All right. Most of the elections in OSPF are going to be non-preemptive, and that's to promote stability within the routing domain. Router IDs are used as link IDs for a lot of the different LSAs. It's used for establishing the DR and BDR election process. So we don't want that router ID constantly changing. We want to make sure that it stays consistent. So let's go ahead and set the router ID on this guy to 2.2.2.2. Do a clear IP OSPF process. Yes. And we'll do the same thing on router 3. Router OSPF 1. And we'll say router ID, in this case, 3.3.3.3. And do a clear IP OSPF process. It is highly recommended that you manually configure the router ID, even though it's not technically necessary. Because again, that means that you have something that's more predictable and more consistent. But let's just review real quick the router ID. It's a fundamental parameter in OSPF. To start the OSPF process, you have to have a unique router ID, which means you have to have at least one primary IP address on an interface in the up state. Otherwise, you're going to get a message that says, hey, the OSPF process can't start. Now, the selection criteria for the router ID is as follows. If the router ID is manually configured, that will take precedence over everything else. If there is no manually configured router ID, then it's going to be the highest IP address on an active loopback interface. And then after that, if you don't have any loopback interfaces, it's going to be the highest IP address on all of the active non-loopback interfaces. All right, they do not have to be running OSPF. They don't have to be running OSPF, but they do need to be in the up state. Okay, after those 3 steps, if we cannot select a router ID at that point, we're going to see a syslog message indicating that the OSPF process fails to select a router ID and that the OSPF process basically can't function at this point. All right. So we cleared the OSPF process on the routers. Once you've selected the router ID, like I said, it will not change unless you do that. All right. So in a production environment, the OSPF router ID really can't be changed very easily because it does require us to reset all of our adjacencies, which means that we're going to have a temporary routing outage in that process. All right. Because now this router has to originate new copies of all its own link state advertisements with this new router ID. So just be aware of that. When you clear the process, that's what's gonna happen. All right. So we've cleared our processes. Let's go ahead and clear the process on router 1 as well. Even though we kind of aren't. Let's just do this real quick. Show IP OSPF neighbor. And see if router 1 is aware of these new router IDs. I mean, it should be. Show IP OSPF neighbor. Yeah, we see all the router IDs are consistently configured. 4.4.4.4, 5.5.5.5, 2.2.2.2, and 3.3.3.3. All right. So our next step then is to kind of go through the process of verifying OSPF functionality. Now, naturally, one of the very first things that you're going to want to do is you're going to want to check for neighbors, because the very first thing that happens in any dynamic routing process, whether it's BGP or EIGRP or OSPF, is that in order for us to exchange information, we have to have an adjacency. We cannot exchange information without an established adjacency. Now, I could do it this way. I could simply say show IP protocols, and I can see that I'm running OSPF process ID 1. I have no outgoing or incoming filters. We'll talk about that later on in the course and also in the advanced routing course. The router ID for this router is quad 2. We have one area. It's a normal area. We're not running any kind of special area types in this case. Maximum number of routed paths is 4. Routing for networks. This indicates how the network statements were actually entered into the configuration. I would say if it was done on the interface, let's go to router 3, for example, and do a show IP protocols. All right, you can see here that we actually enabled the protocol directly on the interface in this case, and you can see it indicates that, configured explicitly on the loopback interface. So this routing for networks is how we entered our network statements, and this indicates that we actually configured the protocol directly on the interface. All right. So we can verify that with show IP protocols. Of course, we can also investigate the neighbor table. That's really, really critical. Show IP OSPF neighbor. We talked about this quite a bit in the lecture series, right? There are 3 data structures, 3 primary data structures that exist in any dynamic process. You've got your neighbor table, you've got your topology database, and you've got your routing information table or routing information base, your global RIB, right? Well, the topology table, or in the case of OSPF, the link state database gets populated by information from the neighbors. So if I don't have neighbors, I'm not going to learn anything. Makes sense to go ahead and kind of verify the neighbor relationships first. Router 2 has a neighbor with router 1, and router 3 should also have a neighbor with router 1. Show IP OSPF neighbor, and it does. Okay, so let's talk a little bit about what we're seeing in this particular table here. Right, this is obviously going to display neighbors on a per interface basis, so interface Ethernet 1.0 in this particular case. The neighbor ID simply represents the router ID of that particular neighbor. The priority represents the interface priority. This is used for the DR/BDR election process on multi-access networks. The default is 1, the maximum is 255. The higher the priority, the more likely it is that you're going to become a DR for a particular multi-access segment. It's not guaranteed, because again, it's a non-preemptive process. So if somebody else boots up before you do, even though you may have a better value, you're not going to become the DR. But the default is 1. So there's a tiebreaker. We'll talk about that a little bit later on. If the priority were 0, that means there is no DR/BDR election, or you will never become a DR/BDR. It means you're basically ineligible. Okay? The state represents the state of your relationship with that neighbor. Router 1 is the DR. It's not your state to router 1, it's router 1's state to you, and we have a full adjacency, which means we've gone through the XStart state, we've gone through the exchange state, we've gone through the loading state, we are now fully adjacent, and our link state databases are the same. That's a very, very important concept in OSPF. OSPF routers have to have, within the area, have to have a common database. It's very, very important. It's actually very critical. All right. Now, you might see a hyphen. So we see a hyphen in this particular case. We see a 0 here. That is because this is a serial link. And if I did a show IP OSPF interface serial 20, you'll notice that by default, OSPF counts a serial link as a point-to-point link. There is no DR BDR election on a point-to-point link. So there's no reason to do, we only have another adjacency, right? It's point-to-point, literally one router connecting to another. So there's no way to reduce the number of adjacencies that we're going to have on that link because it's just not possible, right? There has to be at least one neighbor. So for those point-to-point network types, remember there's 5 different network types: broadcast, non-broadcast, multi-access, point-to-point, point-to-multipoint, point-to-multipoint, non-broadcast. Loopback is also one, but we don't typically talk about that one too much. All right? So we don't do a DR-BDR election. We still have a full adjacency, but there is no DR-BDR election actually on any point. Point-to-multipoint, non-broadcast, point-to-point, point-to-multipoint, no DR-BDR election. Anything that's point to anything, no DR-BDR election. All right? And we'll talk again why router 1 became the DR. We can actually see from this show IP OSPF interface output right here, show IP OSPF interface output, we would actually see a DR and BDR listed as well if this was a multi-access network. So going back to our neighbor table here, the dead time indicates how long I'm going to wait before I expect to get a hello packet from that peer. And if I don't get a hello packet within that time frame, I'm going to consider that the neighbor is dead and no longer communicating, and I'm going to go ahead and delete that neighbor. Now you'll notice that this timer doesn't really go below 30 seconds, right? In fact, it goes down to 30 and then it jumps back up to 39. That's because the default timers for OSPF on this type of network, in this case it's a point-to-point network, is 10 and 40, excuse me, 10-second hello timer, 40-second dead timer. So we should never really see this number go below 30 in that particular case. The address column, or this address field, represents literally the neighbor's IP address, and then the interface represents the exit interface that I go out of to get to that particular peer. Now, another very, very useful command for OSPF is show IP OSPF interface. This is a really, really useful command because it gives us all kinds of wonderful information. It tells us the address, of course, on the interface, what area the interface is participating in, what is the OSPF process it's included in, what is the router ID, what is the network type. Now, this network type directly affects how OSPF treats the interface. You'll notice that the timers here, 10 and 40. We'll talk about the wait timer a little bit more. The wait timer is kind of like when a router fails, can it claim the role as the BDR again? When it comes back immediately, it has to wait 40 seconds if it wants to become the DR again. But we'll talk about that a little bit later on. We can see here the cost of the link, which is 64. Remember, it's just basically 10 to the power of 8 divided by the link bandwidth in bits per second, right? In this case, 64, because it's a 1.544 megabit per second link. So if I take 10 to the power of 8, 10 to the power of 8, and I divide that by 1544, now it's in bits per second, we get a cost of 64. Remember, there's no floating point math in these calculations. We don't round up, we simply drop the remainder, and that becomes the cost of the interface. So that's how this cost was calculated at 64. We can also see how many neighbors we have on this particular peer, who the neighbor is. So this is a really, really helpful command to give us a lot of really valuable information about what's happening on that particular network. Okay? Now, if I look at the topology diagram here, because really the next step would then be to go and look at the actual routing information base, the global RIB, if you will. Now, if I'm looking at this from router 5's perspective, router 5 has this connected network 145, but it should be learning about the 4 network inside of area 0. So that should show up as a type 1 route, which is an LSA type 1, O route, an OSPF route. I should also be learning about the 12 and the 2 subnets from another area. Those are called inter-area routes, or type 3 LSAs. So those should show up in my routing table as OIA. And then I have the 13 and the 3 subnets as well that should also show up as OIA. So let's go ahead and go into router 5, and let's take a look at our routing table. Show IP route. OSPF. All right. And as suspected, we have our O route here. That's our 4.0 subnet. We've got our 3.1. Now this is coming in as a 3.1 because we didn't change the network type. Even though it's configured as a /24 on the interface, because it is a loopback network type, OSPF automatically always advertises loopbacks as a host route, regardless of whatever's configured on the interface. We could change that behavior by actually going and changing the network type under the interface. We also see the 13 and the 12 subnets, and then the costs that are associated with these are just the cumulative path costs for each of those networks. All right, so among the routes that originated within OSPF, OSPF clearly distinguishes 2 types of routes, what we call intra-area routes and inter-area routes. Intra-area routes are the routes that are originating and learned within the same local area. The character O, in this case, does indicate that this is an intra-area route in the routing table. The second type of route is an inter-area route, and that's originating either in other areas or it's inserted into the local area from an ABR, an area border router. And those are going to be indicated with an OIA route or an OIA code in the table. All right. Now there are many different types of routes that can come into OSPF. There's external type 1, external type 2, NSSA routes, NSSA type 1 and type 2, and so on. But the primary concept that we're just focusing on right now is the idea of the kind of inter-area versus intra-area routes. All right. Now we are going to do some other exercises a little bit later on where we're going to talk about other types of routes that exist as well and how those routes come into OSPF. And if you ever get a chance to get into my CCIE mentorship program, we go into it in even more detail in that program as well. All right. So we get the 4.0 prefix. That's an example of an intra-area route in this case, from at least from router 5's perspective, because it's a route that originates on router 4. The prefixes from R2 and R3, they're part of area 1 and area 2 respectively. They're going to be shown up in the routing table as inter-area routes. Now let's take a look at the database here. Actually, let me just make one more point here. Like I said, on the other routers, router 2 and router 3, the loopback interfaces are configured as 2.0/24 and 3.0/24. But again, because they are loopback, OSPF by default is only going to advertise the subnets that are on loopback interfaces as /32 routes. To change that behavior, you can go in and change the network type on the actual interface. So I could come into router 3 here as an example, go into interface loopback 0 and say IP OSPF network. And we could change that network to point to point. All right. Now, if I do show IP OSPF interface, loopback 0, we can now see the network type is point to point. So it's going to treat it like kind of a regular point to point circuit. But if I go back to router 5, and I look at the routing table now, you can see that this network is now being advertised with a /24 prefix. Not that that's really something that has to happen, of course, because it is in fact a loopback. We're using these loopbacks in our particular topology just to simulate some additional subnets. That's really the main goal here, but the reality is that we're just trying to kind of represent the network as it is configured. Now, obviously, we've looked at our neighbors, we've looked at show IP protocols, we've done our basic connectivity checks. The next thing that we do is we need to observe what the topology database looks like. If I go into router 5, for example, the link state database, and I do show IP OSPF route, in this particular case, we're going to take a look at basically what is a distinction between what we have our list of intra-area routes and inter-area routes. All right. This output gives us really, really critical information. It tells us who the area border router is. What is the router ID of that area border router? What is the IP address of that area border router? What interface is that router using to advertise routes into the area, and so on. Now, for inter-area routes, the metric of the route, the cost of the route, is basically the area into which the route is distributed, and then the interface over which the route is inserted, and that's actually displayed here as well. So if you take a look at this output here, we have our backbone area, which router 5 is participating in, and these are the routes that are listed in the backbone. Now, this is interesting because this is very similar to what you would see in a BGP table. Asterisk indicates that it is a valid route, right? Greater than symbol indicates that it is the best route, and it's actually going into the global RIB. Why would this particular route not have a greater than symbol? Because it's being inserted into the routing table not as an OSPF route, even though it shows up in the OSPF database. It's being inserted into the routing table as a connected route, because connected routes have a lower administrative distance than OSPF routes, right? Connected is 0 and OSPF is 110. Here's the area border router. This is the cost to reach the ABR. As I was mentioning, this is the interface I use to get there. This is the exit interface. This is the area that it's attached to. This is how many times the SPF algorithm has been calculated. And then these are all the inter-area routes that show up, right? So basically, these are all the routes that this ABR is presenting to the area. All right? Now, from a neighbor perspective, OSPF routers, as I've mentioned in our previous lectures, go through different states before becoming fully adjacent, if you will. Right? The down state, meaning that I have no active neighbors detected. The init state, meaning that a hello packet was received from the neighbor, but I didn't see my router ID in the neighbor list within that hello packet. The two-way state, same thing, I received a hello packet, but the only difference here is that I also see myself listed as a neighbor in that list. The extart state, that's where we're doing our master-slave negotiation between the routers. We're trying to determine what the master role is and what the slave role is between the routers. The exchange state, this is where we're exchanging a summary of our database, right? A summary of our link state database so that we can determine what types of routes need to be learned, what types of routes need to be processed, right? So stuff that I have that you may not have, or stuff that you have that I don't have, that's where we're going to go into the loading state. The loading state is where we're actually exchanging the link state requests and those link state updates, and then finally the full state, right? So again, just to summarize, the down state, no information has been received on the segment at all. The init state, like I said, the interface, we detected a hello packet from a neighbor, but bidirectional communication has not been established yet. In two-way, we have bidirectional communication with the neighbor. I see myself in the hello packet coming from that neighbor. If you look at a hello packet, let's take a look real quick. Let's go over to our link here, and I'm going to go into router 5, and I'm going to start a packet capture here. We'll let that load, but basically what's going to happen is I'm going to be seeing myself listed in your hello packet as a neighbor. That's why we form this two-way state. That means that we could potentially become full. We may stay in a two-way state. In our particular topology, that's not going to take place. But if you had, say, 5 or 6 or 7 different routers in a common subnet, not all those routers would move beyond the two-way state. So let's see, this is a hello packet from router 4. And again, if I go in here and I look at the hello packet, these are the neighbors that are listed. So I see myself listed as a neighbor, which means that I know that we are now in the two-way state. Okay? So when routers are in the two-way state, they have to decide whether they're going to proceed to building a full adjacency. That decision is going to be based on whether one of the routers is a DR or a BDR, whether or not it's a point-to-point link or a virtual link or something like that. So there's several different factors that would affect whether or not we're going to go beyond that two-way state. If we do, we go into the extart state. That's where we try to establish that initial sequence number that's going to be used in the information exchange packets. That sequence number makes sure that the routers always get the most recent information. One router will become the master and the other will become the slave. The master router will poll the slave for whatever information it needs. And then that's also where database descriptor packets are going to be exchanged. I'm not sure that we would see any of those in this case because we've already kind of gone through the adjacency process, right? There was an update, there was an acknowledgement. We only see that as I could clear the process, I suppose. Let me go to router 5 and do a clear IP OSPF process. And what we should see is we should see us transitioning through these different states. We should see the different packet types. So we see here's our DBD, that's our database descriptor. So we are getting our hellos. This database descriptor is where I'm basically getting a summary of the database, if you will, kind of, am I the master? Are we exchanging routes? And then we see our link state information here, our type link value fields here that reference some of the different options. So we're kind of going through this process. Now, if we were to do this and take a look at this as a debug, you would see the process in the router as well, kind of going through the process of the adjacencies. So let's go into router 3, for example, and let's do a debug IP OSPF adjacency. And we'll do a clear IP OSPF process. And we should see also us transitioning through these different states here, right? So we can see here that we went into the, there we go, sorry, down state, right? Interface went down. Here we're in the two-way state, right? And now we're doing our DR, BDR election. So that means that we're kind of moving into the extart state, right? We're sending and receiving database descriptors. By the way, these packets are sequenced and acknowledged. We would see the acknowledgments in our Wireshark capture. So we're saying, okay, we're the master, and then we can see where we've done our exchange state. Notice also in the exchange state that this is where, the extart state is where we see the MTU being exchanged. That's pretty critical as well, because if there's an MTU mismatch, this is the state in which we're going to be able to identify that particular mismatch. Let's do an undebug all. So during the OSPF adjacency process, right, we establish the adjacency in several different steps. The first thing the router does is it tries to establish a full OSPF adjacency with neighbors by exchanging hello packets. Both OSPF neighbors are going to start in the down state. That's always the initial state of the neighbor conversation. And like I said, that indicates that no hellos have been heard from a particular neighbor. When a router receives a hello from a neighbor, but hasn't seen its own router ID in that hello packet, it transits to the init state. All right? The router says, okay, I do see somebody else, but we don't necessarily recognize that we could become adjacent and we don't see each other's router IDs. So it is going to record the router ID, and it's going to start including that neighbor's router ID in the hellos that it sends to the neighbor. When the router sees its own router ID in the hello packet that it receives from the neighbor, it transitions to that two-way state, and that's what we see right here, right? If we were to actually kind of correlate this to a Wireshark capture, we could see that in the Wireshark capture as well. That means that basically bidirectional communication with the neighbor has been established at this point. Now, on a broadcast network, which is what we have in this particular case, we do our DR-BDR election. And we can kind of see that process kicking off here. Backup scene event before wait timer. That's that wait timer that we saw that I referenced. Basically, when a router loses its role as the DR, it has to wait for a specific amount of time before we kick off that BDR election process. So it's very possible that a router that loses its DR status could in fact become the BDR, even though there might be another router that's already elected as the BDR because of that wait timer. Some we'll talk about maybe a little bit later on as well. Okay, so we're going through this DR-BDR election. 1.1.1.1 is elected as the DR. 3.3.3.3 is elected as the BDR, which actually doesn't make a whole lot of sense, right? Because if we go based on what the election process is, well, it's the highest router ID, well, the highest priority, and we'll assume that the priorities are all the same, so it would be the highest router ID. Well, guess what? Router 1 just happened to be the first router that we started OSPF on in this particular segment. So it became the DR automatically, and because it hasn't failed, it stays as the DR, right? It's not going to lose its role as the DR. All right? Again, a non-preemptive election process in this particular case. All right? Now, the whole concept of the DR-BDR election is to optimize the exchange of routing information on our broadcast network. In our next task, we'll kind of go into more detail about that. All right? In the next step, the routers start to exchange the contents of their database. The first part of this particular process is to determine who the master slave is and choose that initial sequence number for that adjacency formation. In order for us to accomplish that, the routers exchange something called DBDs, or database descriptor packets. When a router receives an initial DBD packet, it transitions the state from the packet that it received for that particular neighbor anyway to what we call the exstart state. So it populates its database summary list with the LSAs that describe basically the contents of the neighbor database, and it sends its own empty DBD packet to the neighbor. The idea here is that we're trying to, in this DBD exchange process, we're trying to establish, first of all, who's going to be the master. That's going to be the one that's going to have the highest router ID. And it's going to be the only router in this case that can actually increment the sequence numbers during the exchange, by the way. Once that master-slave election process is complete, the database exchange can start. And that's where we move into the exchange state. Now, the exchange state is a little bit misleading, the name itself, because you think exchange, well, that means I'm exchanging routing information. It's actually not the case. We're exchanging a brief description of the database that we have, which contains basically only the headers of the LSAs in what we call a database summary list or a database summary, right? So it gives a description of all the LSAs, but not the full content of the OSPF database. Because guess what? You might already have a bunch of stuff that you may have received from other routers, so you don't need everything. And I might have a bunch of stuff that I received from other routers as well, so I don't necessarily need everything. So rather than just arbitrarily exchanging everything that we know, we exchange a summary of the database, and then once we've identified what's missing, what are the differences between the databases, we add the missing LSAs to something called a link state request list, and at that point we move into the loading state. So router 3 in this case is going to send a link state request packet to the neighbor requesting the full contents of those missing LSAs from that link state request list. R1 is going to reply with a link state update which contains the full version of those missing link state advertisements. Okay? Finally, after that's all said and done, we move into the full state. Both neighbors transition to the full state. That means that the databases are now synchronized and the neighbors are fully adjacent. All right? So it's a very, very complex process, much different than what we saw with EIGRP. And in the case of EIGRP, it was mainly, hey, let's just become neighbors and exchange everything, right? Now, as far as this multi-access network goes, and we do have one multi-access, actually a couple multi-access networks here. This one here in area 0, this is actually technically a multi-access network as well, even though there's only 2 routers on that segment. So there's going to be a DR-BDR election. This always occurs, by the way, on multi-access broadcast networks and non-broadcast networks, so MBMA networks. The DR-BDR election process is supposed to improve the network function by reducing the amount of routing update traffic that has to be generated and by managing that link state synchronization. Right? So in our full topology, you might have 3 or 4 or 5, 6 different routers, but the adjacencies are going to happen, the full adjacencies are going to happen between the DRs and the other routers and the BDR and the other routers. But the actual synchronization topology is only going to come from the DR. All right, so the DR within the segment, this election is done per broadcast network, per multi-access network. The DR is responsible for propagating that information. All right, so a multi-access network is a broadcast network, something like Ethernet, or it could be like a non-broadcast network like Frame Relay. But there's an interesting problem with OSPF in this case. All of the routers sharing a common segment are going to be part of the same IP subnet. So if we're forming an adjacency on a multi-access network, every router will actually try to establish a full OSPF adjacency with all the other routers on that particular segment. All right? Now in our network here, that's probably not a big deal. We only have a couple of different routers, but it could represent a much bigger problem if we have a very, very large broadcast domain, or if we're running some sort of NBMA network where we don't have maybe a full mesh, right? We're running a hub and spoke or a partial mesh topology, and so on. So the issue, particularly with NBMA, non-broadcast multi-access networks, is that those spoke routers don't have the ability to form a full neighbor adjacency, and they can't synchronize their OSPF databases between themselves, right? So basically you want to have a central point, the hub router in this particular case, that is responsible for that database synchronization and advertises that information to all the other segments and all the other routers. Now, additionally, as the number of routers on the segments grow, the number of OSPF adjacencies are going to increase exponentially. Every router would have to potentially synchronize its database with every other router. And if you have lots and lots of routers on a segment, it's going to be very, very inefficient. All right. And another issue that comes up too is when every router on the segment advertises all its adjacencies to the other routers in the network. So if you have a full mesh of OSPF adjacencies, the other OSPF routers are going to receive a large amount of redundant link state information. All right. Again, this is something that's going to cause issues with CPU utilization, network bandwidth utilization, and so on. So it's much better to kind of establish a central point where all the routers form that full adjacency. They're going to advertise their information to that router, and then that router is going to be responsible for advertising that information to the rest of the network. This is where the DR-BDR election process comes into play. All right. That's what provides that centralized communication. Reduces the amount of routing update traffic, manages that whole, and we manage that whole link state synchronization. Now, to reduce the routing update traffic, the DR and the BDR act as that central point of contact for all of the link state information that's being exchanged on that multi-access network. So each router in the topology is going to have to establish a full adjacency with the DR and the BDR. The BDR is really there to act as a backup, of course, if the DR fails. All right? So rather than exchanging link state information with every other router in the segment, we send that link state information to the DR and the BDR by using a dedicated group-specific multicast address in IPv4 that's 224.0.0.6. In IPv6, it's FF02:6. The DR represents that multi-access network in the sense that it basically sends link state information from each router to all the other routers within that broadcast domain. So this is going to greatly reduce the amount of overhead and the amount of router-related traffic on that segment itself. All right? If there's a topology change, if something changes, guess what happens? The router is going to notify the DR. The DR is then going to propagate that information to the rest of the networks in that segment, in that broadcast domain. So let's take a look at router 1, router 4, and router 5. Those are the three routers that we're sharing a common segment here, and see if we have a synchronicity here as far as the DR-BDR election. Show IP OSPF neighbor. And in this case, we can see that from router 1's perspective, and again, we're looking at this in this multi-access network here, so I'm focused primarily on router 4 and router 5 in this case. All right, so router 1's perspective, router 4 is the DR in this particular case, and router 5 is the BDR, which means that router 1 must just not be any of those, right? It's not the DR or the BDR, which means it's a DR other. So if I go over to router 4, I should see a similar output here. Show IP OSPF neighbor. And sure enough, router 1 is a DR other. That means it's not the DR or the BDR. Could potentially be one, but it's not. Router 5 is the BDR. And again, you look at this and you go, well, wait a minute. Router 5 has the highest router ID, but again, it's just a matter of when the routers establish their adjacency and so on. So this is not really a concern in most modern networks in the past, outside of dealing with, of course, the NBMA networks where we might not have a full mesh. If it's a standard broadcast network, we're not really concerned about who becomes the DR or the BDR because, quite frankly, it doesn't really matter, right? In the past, we might have been more concerned because you might have some routers that are maybe not as efficient or don't have as much processing power or whatnot. They can't process that information. But typically, we don't really concern ourselves with this too much. All right? Like I said, when these routers first start to establish their adjacency, they're going to send those hello packets to discover the OSPF neighbors, which one are active, which one are in a common segment. Once that bidirectional communication between the routers are established, they go through that DR-BDR election process. We already talked about the IPv4 and v6 address that's used to communicate to the DR and BDR. We have a multicast group address as well for all other routers. It's called the All SPF Routers Multicast Group. It's 224.0.0.5 or FF02:5, and so on. So again, the procedure of the DR-BDR election occurs actually not only when the network first becomes active, but we go through the election process again if the DR fails or goes down. The BDR immediately becomes the DR, and then we start the election process for the new BDR, right? So in this particular case, router 1 might become the BDR. If let's say router 4 is the DR in this case, right? Router 4 goes down, router 5 is going to become the DR. Now, router 1 doesn't actually immediately become the BDR in this case. There's a wait time. And as long as that other router comes back, if router 4 comes back within that wait time window, router 4 would actually become the BDR, and router 1 would maintain its role as a DR other. But if that wait timer expires, router 1 would actually take over the role as the BDR in this particular case. So let's go ahead and go on router 5, show IP interface brief. And I'm going to shut down Ethernet 1.0. Actually, we're going to do this on router 4 because router 4 is the DR. Show IP interface brief. And let's go into interface Ethernet 1.0. We're just going to shut that interface down. Now you'll notice on router 1, if I do a show IP OSPF neighbor, I can see that in this particular case, well, actually, we do have a switch in between. So we need to wait for the dead timers to expire. That's why BFD, bidirectional forwarding detection, is a good thing to have, because we're going to have to wait for that 40-second timer to expire. It looks like we're down to 9 seconds, 7 seconds, 6, 5, 4, 3, 2, 1. We lose our adjacency with router 4, and router 5 immediately becomes the DR. Now, if I go ahead and bring that interface back up, and the adjacency reforms, and if I go back to router 1, I can see in this particular case, well, I guess I didn't do it quickly enough. Router 4 actually became a DR other. Router 5 is the DR, which means router 1 must be the BDR in this particular case. All right, but you can see how that process kind of is just automatic. That election process happens automatically. All right, but again, it's non-preemptive, meaning that just because router 4 came back and it was the DR previously, it's lost its role as the DR, and it kind of just has to wait now until router 5 fails, and in this particular case, until router 5 and router 1 fail. All right? So just something to keep in mind in this particular case. When we, in the past, we would maybe possibly try to modify configurations to force a particular election, but we don't really concern ourselves with it too much unless we have a very specific topology-based requirement where it requires us to specify a specific router is never going to be elected because maybe it's a spoke router in a hub and spoke environment and so on. All right. Now, like I said, we can use the priority to influence the election process. The priority is actually the first value that's looked at. The router with the highest priority is typically elected as the DR. The second highest priority, the BDR, and so on. And if there's a tie, we're going to go ahead and use the router ID as the tiebreaker, because there should never be a duplicate router ID, obviously, in this case. All right, and the highest wins in that particular case as well, the highest router ID. So let's say I go to router 1, and let's do a show IP interface brief. And we're looking specifically at Ethernet 1.1, so interface Ethernet 1.1. And I'm going to say IP OSPF priority, and in this case, I'll set the priority to 100. Now, if I go to router 5 and I do a show IP OSPF neighbor, I see that priority get advertised pretty much immediately because it's part of the hello packet advertisement. But you'll also notice that router 1 still did not become the DR, even though it's advertising a far superior priority in this particular case. Now, router 4 is the DR other, which means router 5 is the DR. So if I do a clear IP OSPF process in this case, naturally router 1 is going to become the DR in our particular case. And again, it would have anyway because it was already the BDR in this particular case. So I guess the bottom line is we don't really have complete control over who the DR becomes. I mean, we can probably kind of influence that initially, maybe by booting routers up in a specific order, maybe setting some priorities on some routers to 0 so they can't be elected. But usually we don't really have too much control because a router might reboot or might lose connectivity temporarily, forcing an election. And then we just allow that to be the new norm, if you will. Okay? All right, so I can go into router 1 now and I can say, okay, who is the DR and the BDR? If I do a show IP OSPF interface, Ethernet 1.1, I can see for this particular network, the BDR is router 5, the DR is router 1. So that's a very useful output there as well because it gives me an indication of who's actually the DR and BDR. All right, very, very useful output in this particular case. Now I could do this. I could go into router 4 as an example and I can say, let me make sure I'm in the right interface, which is 1.0. And I can say IP OSPF priority 0. And I could actually technically do the same thing on router 5. Interface Ethernet 1.0. IP OSPF priority 0. Do show IP OSPF neighbor. We can see that router 4 has a priority of 0. And we only go into the two-way state because it's not a DR or a BDR, so we're going to stay in that two-way state. We still recognize that router 4 could potentially, well, in this case it couldn't be, but could potentially be a full peer, but in this case that's not going to be the case. Now, this is a big problem, right? If router 1 fails in this particular case, the network's going to fail because we can't elect a DR. Let me go to router 1 because router 1 will really show us show IP OSPF interface or show IP OSPF neighbor. And we can see that both router 4 and router 5 are listed as DR others. Now, we're still exchanging information, right? Because we still have a full adjacency. But that's because router 1 is the DR. You do want to be careful with that, of course. All right. So one of the last things that we'll talk about, we actually have two things that we're going to talk about to finish up this particular discovery, is what happens if there's an MTU mismatch on a segment, right? MTU related OSPF issues. And then we'll wrap up this lesson by taking a look at the timers. We know that the IP MTU determines the maximum size that a packet can be forwarded without performing any kind of packet fragmentation. The problem with OSPF is that because we're exchanging database information, which is encapsulated into fairly large PDUs, if there's an MTU mismatch, we can have inconsistent OSPF databases. So OSPF actually by default requires that we have the same MTU on both sides of a link. All right? Any OSPF neighbors that have a mismatched MTU, they're actually going to get stuck in the Xstart state. So the IPMTU parameter, that's what we do on an interface. We use the IPMTU command. That determines the maximum size of an IP packet that can be forwarded out of an interface without the use of packet fragmentation. If a packet with an IPMTU larger than the maximum value that's set arrives on that interface, it's either going to discard that packet if the do not fragment bit is set in the packet header, or it's going to fragment that packet. Well, here's the problem. OSPF packets completely rely on IP for fragmentation. There is no transport layer functionality. All right? RFC 2328 says you should not fragment OSPF packets. There you could have some situation arise where the size of the OSPF packet does have a greater value than what the interface MTU is, and so fragmentation would have to occur in that particular case, but it's generally recommended that we try to avoid that. If there is an MTU mismatch between neighbors, we see issues with the exchange of link state packets, and then we might have some sort of continuous retransmissions of packets and so on. So basically the bottom line is OSPF says, you know what, by default, we're simply going to require that you have the IPMTU configured on both sides of the link. If it doesn't match, we're going to get stuck in that Xstart state. So let's go to router 3 in this particular case, and let's change the MTU. We're going to go in interface Ethernet 1.0, and we're going to say IP MTU, and we'll just change it to 1400. The default is 1500. All right, so we change the MTU size. That's going to create an MTU mismatch between those peers. And if we do a debug on router 3, so let's do a debug IP OSPF adjacency, OSPF adjacency, and then I do a clear IP OSPF process, we should see an indication that there's an MTU mismatch. And we see that actually right here. So we see received a DVD from 1. The MTU is 1500. It's larger than my interface MTU. Received a DVD, larger. Notice we're xstart, 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 xstart. So we're basically stuck in this xstart state because of this MTU mismatch. All right, remember that DVD packet carries information about the largest non-fragmented packet that can be sent from the particular neighbor. So in this particular situation, the IP MTU values on different sides of the link aren't equal. R3 is going to receive a DVD packet with an MTU size of 1500, which is greater than its own MTU size of 1400, and that's going to result in the inability for router 3 and router 1 to establish an adjacency. All right? Now, we could do a show IP OSPF neighbor. We would see that reflected in that neighbor output as well. All right? Remember, mismatch interface MTU sizes on the opposite side of the OSPF link will result, or could result, I should say, well, it will result in the inability to form a full adjacency, but you can override this behavior. I'm going to show you how to do that in a second. All right? Now, Cisco's recommendation is to go ahead and fix the issue, right? There is a command, though, that you can execute that says, I'm going to go ahead and ignore this. It's IP OSPF MTU ignore. All right. So you'll notice here it says the neighbor's down. We're doing the ignore on one side of the link. We need to do the ignore on the other side of the link as well. So let's go to router 4 and let's do IP OSPF MTU ignore. And the same thing on router 5. IP OSPF MTU ignore. And we should see our adjacencies come back up based on that MTU ignore. And sure enough, we see the adjacencies come up. So basically, we're telling OSPF, you know what? Yeah, I get it. The MTUs don't match, but we're just going to ignore that, and we're going to continue to form our adjacency. I think I did the wrong routers, but you get the idea. Okay. Router 3 came up. Make sure I look at my topology. Router 1. Yeah, I should have an adjacency with router 4 and router 5. Do show IP OSPF neighbor. Yeah, I do have a full adjacency. So I didn't see down, I didn't see those come to loading to full. But yeah, we do have a full adjacency, even though there is an MTU mismatch in this particular case. Again, not recommended. The recommended solution is to fix the MTU problem, right? To make it match, in other words. All right? So the last thing we're going to talk about is how do we manipulate the timers themselves. Unlike EIGRP, which we talked about in our previous lessons, OSPF, the hello and dead timers, have to match. All right? The default values on broadcast networks and point-to-point links, it's going to be 10 and 40 seconds. On all other OSPF network types, the hello interval is going to be 30 seconds. The dead interval is 4 times that value, in this case 120 seconds, and so on. All right. Now you could do, say, a debug IP OSPF hello to see the timer mismatch. Just like EIGRP, we use 2 timers to check the neighbor reachability, and those 2 timers are the hello interval and the dead interval. Now, the interesting thing about OSPF, and this is why it's really important to understand, is that the network type determines the hello timer. All right? So for multi-access broadcast and point-to-point links, 10 seconds. Non-broadcast multi-access, point-to-multipoint, point-to-multipoint non-broadcast, 30 seconds. All right? So I could potentially come into an interface, for example, and change the network type, thinking I'm fixing maybe a DR-BDR election problem or whatever, but I might inadvertently break OSPF because the timers don't match. Say, for example, in this case, R2 is on a point-to-point link. Now, I could come into R2 and I could set it to point-to-multipoint, right? If I do a show IP, well, I have it right here, right? It's point-to-point. I was going to do a show IP OSPF interface. Serial 20 is point-to-point. These are the timers. So I can go into interface serial 20. Maybe this is a multi-point interface in a hub and spoke frame relay environment. So I would say IP OSPF network point to multipoint. If I do show IP OSPF interface serial 20, you'll notice here that the timers changed from 10 and 40 to 30 and 120, which means I lost my adjacency. Now, there's 2 ways to fix this problem. You could change the network type back, but that might not work for whatever topology you're configuring, or you can set the timers on the interface manually to match whatever timers you would want on the peer. So I can come in the interface and I can say IP OSPF hello interval 10. All right. Now, it should automatically calculate the dead interval at 4 times. EIGRP doesn't do that, but OSPF does. Notice I got my adjacency back. So the network types do not have to match between the interfaces. In fact, network types, sometimes we might have a scenario like this, where I've got router 1 and router 3 are connected with Ethernet, but that Ethernet segment is virtually point-to-point. Well, maybe I don't want to do a DR-BDR election, so I would change that network type to point-to-point so that I'm eliminating the need to do a DR-BDR election on that transit link. All right. Now, you could set the dead timer independently if you wanted to, but again, it's not really recommended. There's really no reason to change these timer values unless you have a specific scenario like I just described here, where you might have to change the network type, which then in turn changes the timer values, which would then in turn break the adjacency. All right. A longer hello interval typically means a longer dead interval, which means dead peer detection takes longer and reconvergence takes longer. A shorter hello interval, meaning a shorter dead interval typically, would mean that you would get faster convergence time, but you're going to have more overhead because you're processing more hello packets. My recommendation is not to rely on the hello and dead intervals for dead peer detection, but to use something called bidirectional forwarding detection, or BFD. And that's something we talk about in the advanced routing class. All right. So we'll wrap up this discovery. We got a couple more discoveries actually in the next section, 3 different discoveries that we're going to go through with regard to OSPF. So we'll see you guys in those a little bit later on.